Hello everyone, I am Balaji Rao. Welcome to BR Maths class. This class is all about relations NCERT. Relations topic you learn in class 11th. Relations topic is there in class 12th also. Class 12th in relations one exercise is there. Very important. Reflexive relation, symmetric relation, problems related to it. Complete relations NCERT. Frequently, you will get questions on the topic relations in JEE examinations. Having good knowledge on relations is very important. That's why complete relations. These classes are completely free on YouTube. However, if you want to support your teacher, if you want handwritten notes, if you want practice materials related to this chapter, you can join in this batch for a nominal price. The course link is given in the description. As this video is lengthy, it is difficult to identify where the topic is. That's why timestamps given for this video. If you tap the screen, you will get timestamps for each topic. Watch these videos with a speed of 1.5 to get good experience. Creating these videos takes so much of time, so much of efforts. Please drop a like for this video. If you like the content, please share these videos in your WhatsApp group. In case if you are not yet subscribed to this channel, subscribe. Without much delay, let's begin the class. This is second concept. In this class, what we are going to learn? What is reflexive relation? What is symmetric relation? What is transitive relation? These are very important concepts in this relations topic. Many students confuse a lot to understand these things, but I'll give clear explanation about each relation with more number of examples so that all doubts will be clear in this class only. Understanding these definitions is very important. Let's see what is the definition of reflexive relation. You see, reflexive relation. A relation R on A. A relation R on A, what it means? It means that R is a relation from A to A, right? This we discussed in last class. A relation R on A, that means R is a relation from A to A, is said to be reflexive relation. This relation is said to be reflexive relation. This is important for every, this is important. You don't take it lightly. For every x in set A, order pair x comma x must belongs to the relation. Then we say that relation is reflexive relation. You may confuse little bit here, but you can understand this easily with the help of examples. I'll take set A like this. Set A is 1, 2, 3. R is a relation on A means R is a relation from A to A. When we say R is a relation from A to A, when R is subset of A cross A. So I want to write A cross A now. If you want to write A cross A, how you will write A cross A? See, first I'll take set A 1, 2, 3 cross. Again I'll take set A 1, 2, 3 A cross A. How you will pair with? You take one element in this first set, you pair with all other elements in the other set, like 1 comma 1, 1 comma 2, 1 comma 3. After that you will take this element to 2 comma 1, 2 comma 2, 2 comma 3. Similarly 3 comma 1, 3 comma 2, 3 comma 3. You know that is A cross A. So I'll write A cross A now. This is A cross A. See, 1 comma 1, 1 comma 2, 1 comma 3, 2 comma 1, 2 comma 2, 2 comma 3, 3 comma 1, 3 comma 2, 3 comma 3. You must know how to write A cross. Now, how many relations I can form on set A? The formula is 2 power number of elements in A cross A. That is what? 2 power 9. So, 2 power 9 means 512 relations we can form. Now, I'll take one relation. You observe, I considered a relation. Is it is a subset of A cross A? If it is subset of A cross A, then only we say that it is a relation on A. You see, order pair 1 comma 2, yes, it is there in A cross A. Order pair 2 comma 1, yes, it is there in A cross A. Order pair 1 comma 1, yes, it is there in A cross A. Order pair 3 comma 3, yes, it is there in A cross A. So it is a subset of A cross A. So this is a relation on A. I taken a relation R on A. Now I need to decide this relation is reflexive relation or not. What is the definition? You observe, this is important. Every x belongs to A, order pair x comma x belongs to R. First you come to set A, not to the relation. You come to set A. R is a relation on A. Na? For every x in set A, you take 1 in this set A. You take 1 in this set A. Order pair 1 comma 1 is there in this relation or not? You see here, for 1 belongs to A, I am checking that 1 comma 1 is there in the relation or not? See, order pair 1 comma 1 is there. For 1 belongs to set A, 1 comma 1 belongs to this relation. Can I say that this relation is reflexive relation? Can I say this relation is reflexive relation from this? No. You need to check for every x in set A. Then only you can say that for every x in set A, if order pair x comma x belongs to R, then only we say that this relation is reflexive relation. Suppose 1 is there, 1 comma 1 is there. That means we say that this element passed reflexive test. Now, we will come to the next element because they are asking for every element in set A. Come to the second element 2. For 2 comma 2 is there in this. You observe for 2 comma 2 is there in this. No, 2 comma 2 is not in this relation. So actual condition is what? For every x in set A, x comma x must belongs to the relation. But here 2 is there in set A, but 2 comma 2 does not belongs to this relation. So we say that this relation is not reflexive. This relation is not reflexive. If you want to write the reason, you can write like this. Because for 2 belongs to set A implies 2 comma 2 does not belongs to the relation. Because of this reason, this relation is not reflexive. I hope you understand. Now, I'll name this relation as R2. You observe, is it is a relation on A? When we say R is a relation on A, when this R is subset of A cross A. 1 comma 1 is there in A cross A? Yes. 1 comma 1 is there in A cross. 2 comma 2 is there in A cross A? Yes. 3 comma 3 is there in A cross A? Yes. So this is subset of A cross A. So first point is it is a relation on A. Okay. Now, is this relation is reflexive? Is this relation is reflexive? What is the condition? Condition is for every x belongs to A. This is important. For every x belongs to A, order pair x comma x belongs to the relation. You take here 1. 1 is there in set A. 1 comma 1 is there in this relation? Yes, it is there. That means we say that this element pass reflexive test. Okay. Now come to 2. 2 is there in set A. 2 comma 2 is there in this relation? Yes, 2 comma 2 is there in this relation. So we say that this element pass reflexive test. Okay. 3 is there in set A. 3 comma 3 is there in this relation? Yes, it is there. So we say that this element pass reflexive test. So finally what we say? We say that this relation is reflexive. And one more important point, as this relation is reflexive, while writing the answer, you cannot write that 1 belongs to A implies 1 comma 1 belongs to R. That's why this relation is reflexive. Like that you cannot say. You can write like this. If you want to write why it is reflexive, for every x belongs to A, order pair x comma x belongs to R. That's why this relation is reflexive. Now I'll take one more example to understand this reflexive relation more clearly. You observe, I consider one relation and it is a subset of A cross A. 1 comma 1, 2 comma 2, 3 comma 3, 1 comma 2. Yes, all elements of R3 are there in A cross A. So this is a relation on A. Now I am checking that is this relation is reflexive relation or not. What is reflexive relation condition? For every x belongs to A, this is important. For every x belongs to A, order pair x comma x belongs to the relation or not, you need to check. Okay. Now, as this is a relation on set A, you come to this set A. Here, 1 is there in set A. 1 comma 1 is there in this? Yes. 2 is there in set A. 2 comma 2 is there in this? Yes. 3 is there in set A. 3 comma 3 is there in this set? In this set? Yes. Here, some people will doubt. Here, 1 comma 2 extra is there, na? Because of that, how it will be reflex. That is not the question here. Here the question is this relation satisfying this condition or not. For every x belongs to A, x comma x belongs to relation or not. That much only. You see here for 1, 1 comma 1 is there. For 2, 2 comma 2 is there. For 3, 3 comma 3 is there. So we can say that this relation is reflexive as it is satisfying the reflexive relation definition. So this relation is reflexive relation or not? Yes, it is reflexive relation. Now like this, how many number of reflexive relations we can form? Total number of reflexive relations. We have a formula for that. You see, we have a formula for total number of reflexive relations on A. The formula is 2 power n of A whole square minus n of A. So total number of reflexive relations formula is this one. In this case, how many number of reflexive relations are possible, right? The set A contains 3 elements. Na? So number of reflexive relation on that particular set is what? 2 power n of A is 3. 3 square is 9 minus n of A is 3. That is 2 power 6. 2 power 6 is 64. Like this, on this set, total 64 relations. Here I written 3 reflexive relations. Na? Actually, we can form 64 reflexive relations on this set. I hope you understand about this reflexive relation. Now, we are going to learn about symmetric relation. Definition of symmetric relation. A relation R on A is said to be symmetric relation if for every x comma y belongs to R. You observe this point carefully. For every order pair x comma y belongs to R. Earlier, for reflexive relation, what we checked, for every x belongs to set A. But here in symmetric relation, it is not like that. For every order pair in the relation x comma y comma x also present in that relation, then we say that that relation is a symmetric relation. We'll understand this with the help of examples. You observe, I taken set A as 1, 2, 3. You know how to write A cross A. This is A cross A. Now, I'll take one subset of A cross A to check symmetry condition like 1 comma 2, 2 comma 1, 1 comma 1, 2 comma 3. You observe this is a subset of A cross A. So this R is a relation on A. When we say this relation is symmetric, to check symmetric relation, we will check for every order pair in the relation. That means you come to this. This is 1 comma 2. For order pair 1 comma 2, for order pair x comma y, you need to check y comma x. That means for this order pair 1 comma 2, 2 comma 1 exist in this relation or not. In this relation, 2 comma 1 is there or not, you need to check. You look here, 2 comma 1 is there here. As 2 comma 1 is present here, from this, you cannot say that it is symmetric. Why? Because you need to check like that for every order pair in the relation. Okay. Actually, what happened? This element passed the symmetric test. For 1 comma 2, 2 comma 1 exist in this relation. This element passed the symmetric test. Like that, you need to check for every order pair. For every order pair x comma y belongs to R, y comma x must belongs to the relation. Here you take the order pair 2 comma 1. 2 comma 1 reverse order like y comma x is 1 comma 2. Is 1 comma 2 is there in this relation? Yes, 1 comma 2 is there in this relation. So this element passed the symmetric test. I hope you are understanding, right? Now come to this 1 comma 1. See, x comma y, y comma x. For 1 comma 1, what is y comma x? Y comma x is also 1 comma 1 for this. I hope you are understanding. So here 1 comma 1 for this order pair, 1 comma 1 must present in this relation. Is 1 comma 1 is there in this relation? Yes, here it is. So this element also passes the symmetric test. One important point is this type of elements always pass symmetric test. So whenever this type of element comes, no need to check reverse order 1 comma 1, 1 comma 1 is there in this relation or not. 1 comma 1, 2 comma 2, 3 comma 3, x comma x, this type of elements always pass symmetric test. I hope you understand what I am saying, right? So this element passed symmetric test, this element also passed symmetric test, this element also passed symmetric test. Like that, you need to check for every, right? So here 2 comma 3 is there at the end. For this order pair 2 comma 3, reverse order is 3 comma 2. Is 3 comma 2 is there in this relation? For 2 comma 3, 3 comma 2 is present in this relation. 3 comma 2 is not there in this. So this relation is not symmetric. When it is symmetric, for every order pair x comma y in the relation, y comma x also must present in this relation. Then only we say that this relation is symmetric relation. So what I'll write here, I'll name it as this R1. R1 is not symmetric. Why it is not symmetric? Because 2 comma 3 is there in this relation, but 3 comma 2 does not belong to the relation. That's why we say that this relation is not symmetric. You observe, I taken one relation on this set A. Is this relation is symmetric relation or not? How to check symmetric relation? For every order pair x comma y, y comma x is there in the relation or not, you need to check. So you come to this relation 1 comma 1. See, I said na, a x comma x type elements, a comma a, 3 comma 3, this type of elements always pass symmetric test. No need to check. You see here, this is like x comma y comma x is also 1 comma 1. 1 comma 1 is there in this relation, means yes, here it is. Yes, here it is. So this type of elements always pass symmetric test. So come to this order pair. Is it passes the symmetric test? Yes. Come to this 2 comma 2. Reverse order of 2 comma 2 is there in this. This type of elements always pass the symmetric test. No need to check. Yes, this passes the symmetric test. You observe here 3 comma 3. Yes, this type of elements always pass symmetric test. For 3 comma 3, reverse order is also 3 comma 3. 3 comma 3 is there in this relation. So this relation is a symmetric relation. You please observe this relation. It is a subset of A cross A? 1 comma 2. Yes, it is there. 1 comma 1. Yes, it is there. 2 comma 2. Yes, it is there. It is a subset of A cross A. So this is a relation on A. Is this relation is symmetric on set A? Is this relation is symmetric on set A? How to check? You will check for every order pair in the relation. For every order pair x comma y comma x is there in that relation or not? You observe here 1 comma 2 is there in this relation. For 1 comma 2, 2 comma 1 is present in this relation? No. So this element fails the symmetric condition. If one element fails, directly you can write this is not symmetric. No need to check at the time these things. As 1 comma 2, for every order pair x comma y in the relation, y comma x also must present in this relation. Here, when you identified there is one order pair x comma y, for that y comma x does not belongs to this relation. In that case, directly you can say that relation is not symmetric. I hope you understand how to check given relation is symmetric relation or not. As we have a formula for number of reflexive relations, this is the formula for number of reflexive relations. We have a formula for number of symmetric relations also. Total number of symmetric relations formula is 2 power n into n plus 1 divided by 2. In some other class, I'll discuss why number of symmetric relations is 2 power n into n plus 1 by 2. Now, transitive relation. Actually, it is a bit confusing to many students, but I'll give very good examples. With that, you will never say that transitive relation checking is difficult. Okay, a relation R on A is said to be transitive relation. A relation R on A is said to be transitive relation for every x comma y and y comma z belongs to R. You please observe this part. First, in the given relation, we will check x comma y comma z exist in the relation or not. Here, what point you need to observe? X comma y comma z. You observe this first order pair ends with y, second order pair starts with y. Such type of order pair we'll identify in the relation. If such type of order pair exists in the relation, then we'll look that x comma z is there in the relation or not. X comma y belongs to R and y comma z also belongs to R. Then we will check that x comma z belongs to R or not. Right. Like that, you need to check that for every such pair of order pairs. You can understand this more clearly with the help of examples. You observe, I taken set A as 1, 2, 3. Then I written A cross A. Now, I'll take one relation on this set. I request you to watch this transitive full thing so that you won't confuse. Okay, right? Now I taken one subset of A cross A. See 1 comma 2, 2 comma 3, 2 comma 1, 1 comma 3, 1 comma 3. Yes. So this is a subset of A cross A. So this is a relation on A. Now my question is how to check this relation is transitive or not. To check transitive relation or not, first you need to look for x comma y comma z exist in the relation or not. If such pair doesn't exist, x comma y comma z doesn't exist, in that case we say that it is transitive. Right? Please try to catch this point. It is a catchy point actually. Many students confuse in this. If you identify x comma y comma z in the relation, then you look for x comma z. Further, we will say whether it is transitive or not. In case x comma y comma z, we will find x comma y. respective y comma z doesn't exist in the relation, in that case we say that that relation is transitive. With the examples you will understand that more clearly. Now how to check this? First listen carefully. You check like this. First you take one order pair. Okay, this is like x comma y. Now you see that this ends with 2, right? This ends with 2. Now you observe that any other starts with 2 other than this. Any other starts with 2. You need to check here. Any other starts with 2? Yes, as this ends with 2, this starts with 2, this starts with 2. That means we are able to find x comma y comma z, right? Okay, 1 comma 2 is there. This ends with 2 and this starts with 2. So this is like x comma y comma z. You can understand this is like x comma y comma z. What is x comma z? X comma z is 1 comma 3. Is 1 comma 3 is there in this relation? You please check. 1 comma 3 is there in this relation here. Yes, 1 comma 3 is there in this relation. So for x comma y comma z belongs to R, x comma z is present in this relation. So this relation is transitive. Can we say like that? No, you cannot say like that, because you need to check for every such pair of order pairs. For every such, you just checked only for these two, 1 comma 2, 2 comma 3, x comma z is 1 comma 3. You just checked only for these two. Like that you need to check for every such pair. I hope you are understanding. So here what happened? This ends with 2, this starts with 2. Yes, checked here. Now you can observe this ends with 2, this one also starts with 2. So this is also like x comma y comma z. I hope you are understanding. For every such order pair you need to check. Okay, 1 comma 2, 2 comma 1. In this case, what is x comma z? X comma z is 1 comma 1. Is 1 comma 1 is there in this relation? Is 1 comma 1 is there in this relation? No. 1 comma 1 is not there in this relation. So because of this example, you can say that this relation is not transitive. I hope you understand. When it is transitive, we have to do so much of work. What is that? For every such order pair, you need to look that x comma z is there in the relation or not. When it is not transitive, actually things are easy. Why? Just give the counter example. In this case, 1 comma 2, 2 comma 1 is there in this relation, but 1 comma 1 is not in this relation. Therefore, this relation is not transitive. Like that we can say directly. So what we say finally? I'll name it as R1. R1 is not transitive. What is the reason? Because 1 comma 2 belongs to R, 2 comma 1 belongs to R, implies 1 comma 1 does not belongs to this relation. 1 comma 2 is there, 2 comma 1 is there, but 1 comma 1 is not in this relation. That's why we say that this relation is not transitive. Now you observe I taken one more relation on A. 1 comma 2 is there in A cross A. 3 comma 1 is there in A cross A. So R2 is subset of A cross A. So R2 is a relation on A. My question is this relation is transitive or not? In this transitive, please observe all the examples, then only you can understand this transitive relation. Now, how to check this relation is transitive or not? First thing, come to this 1 comma 2, right? This ends with 2. Now, you check that any other order pair starts with 2 in this. No other order pair starts with 2. But actually, what is the definition of transitive relation? For every x comma y comma z belongs to R, if such order pair exists, then we look for x comma z. If such order pair doesn't exist, in that case we say that that particular order pair passed the transitive test. Here you see this ends with 2, any other starts with 2, nothing starts with 2. So in that case we say that this particular order pair passed the transitive test, right? So for x comma y, we are unable to find y comma z. If y comma z exists, then we will look for x comma z, right? Okay, so this element passed the transitive test. Now you observe this 3 comma 2, right? 3 comma 2, this ends with 2. Any other order pair starts with 3 other than this ends with 2. Now you observe, is there any other order pair other than this which starts with 2? No. In that case, what we say? This satisfies transitive property. I hope you are understanding. If there exists x comma y, y comma z in the relation, then only we look for x comma z. Otherwise, we say that that particular element passed the transitive test. Here, when I am trying to check for this x comma y, y comma z exists or not, we didn't find y comma z. So in this case, we say that this element passed the transitive test. When it comes to this order pair x comma y, any other starts with 2 means there is no other starts with 2. So in that case, we say that this elements also passed the transitive test. So finally, we say that this relation is transitive. Many students confuse such type of examples. Please, you make sure that if for x comma y, y comma z doesn't exist, in that case, this passes the transitive test. Similarly, for 3 comma 2, no other order pair starts with 2 in this relation. So we say that this relation is transitive. So this relation is transitive. This is one of the best example to understand this transitive relation. You observe, I taken one relation on set A. When we say this is a relation on set A, you observe R3 is subset of A cross A or not. 1 comma 1, yes, 1 comma 1 is there. 1 comma 2, yes, it is there. 2 comma 3, yes, it is there. 3 comma 1, yes, 3 comma 1 is there. 1 comma 3, yes, 1 comma 3 is there. 3 comma 3, yes, 3 comma 3 is there. R3 is subset of A cross A. As R3 is subset of A cross A, we can say that R3 is relation on A. Now my question is this relation is transitive relation or not? One very important point. See, how to check relation is transitive or not? First, we'll take this 1 comma 1 and as this ends with 1, we'll look for any other starts with 1 or not. Like that we'll start. But the thing is, whenever we are checking transitive relation for such elements 1 comma 1, 2 comma 2, x comma x, 3 comma 3, such type of elements always satisfies transitive condition. You see here 1 comma 1, this ends with 1. You observe any other order pair which starts with 1. Here this starts with 1. You look here 1 comma 1, 1 comma 2. What is x comma z in this case? X comma z is 1 comma 2. Now you observe 1 comma 2 is there in this relation. Yes, here it is. 1 comma 2 is there here. That's why this type of elements always satisfies transitive condition. You look here, I'll take x comma x and x comma z. What is the condition here? Transitive condition. This ends with x, this starts with x. What is the transitive condition? X comma z is there in this relation means x comma z always present in this only. You observe this x comma z, z comma z. This ends with z, this starts with z. When we look for transitive condition, we will look for x comma z. X comma z is there na here. I hope you are understanding. This type of elements always satisfies transitive condition. This type of elements always satisfies symmetric condition also. I hope you are understanding. So 1 comma 1 is there. This ends with 1. What are the other starts with 1? No need to check like that. Even though if you check, it satisfies. For example, I'll check here. This ends with 1. This starts with 1, right? Now, what is x comma z? X comma z is 1 comma 2. 1 comma 2 is there in this relation? Yes, 1 comma 2 is there in this relation. Okay, this ends with 1. Any other starts with 1? Yes, here it is there. It starts with 1. What is x comma z? X comma z is 1 comma 3. 1 comma 3 is there in this? Yes, here it is. Yes, here it is. So such type of order pairs 1 comma 1, 2 comma 2, 3 comma 3, x comma x, such type of order pairs always satisfies transitive condition. No need to check transitive condition for that particular relation. I hope you are understanding. So this order pair passes the transitive test. Now come to this. This ends with 2. Now you need to look any other order pair is there which starts with 2. Yes, here this starts with 2. Okay, 1 comma 2, 2 comma 3. There exists x comma y, y comma z. What is x comma z? X comma z is 1 comma 3. 1 comma 3 is there in this relation? Yes, here it is. 1 comma 3 is there in this relation. See, you cannot say this relation is transitive because of this example. 1 comma 2, 2 comma 3 implies 1 comma 3 belongs to the relation. That's why this is transitive. If you say like that, it is wrong. You need to check. You need to check for every such pair of order pairs. I checked this passes transitive test. Now I am checking this element, this ends with 2. I am looking that any other starts with 2. This is the only order pair starts with 2. This is x comma y, y comma z. X comma z is 1 comma 3. Yes, 1 comma 3 is there in this relation. Okay, so what I'll say here, I can say that this element passed the transitive test. That's it. Okay, now come to this. Now this ends with 3, right? Now you need to look that any other starts with 3. You see here, this starts with 3, this starts with 3. First, I'll check this with this. This ends with 3, this starts with 3. Now, what is order pair x comma z? X comma z is 2 comma 1. 2 comma 1 is there in this relation? No. So, here you can stop and you can say that this relation is not transitive. Please catch the point. When it is transitive, you need to check for every such pair of order pairs, right? So as we identified one order pair x comma y comma z such that x comma z does not belong to this relation, then we say that this relation is not transitive. So R3 is not transitive. What is the reason why it is not transitive? Because 2 comma 3 is there in the relation and 3 comma 1 is also there in the relation, but 2 comma 1 does not belongs to the relation. Because of this relation is not transitive. I hope you understand why this relation is not transitive. You observe this relation R4. It is a relation on A because 1 comma 1 is there in A cross A, 2 comma 2 is there in A cross A, 3 comma 3 is also there in A cross A. So R4 is a subset of A cross A. So R4 is a relation on A. Now I need to check this relation is transitive or not. See, we'll check for every order pair. You see this 1 comma 1. This is 1 comma 1. This ends with 1. Any other starts with 1? No other starts with 1. And moreover, we know that this type of order pairs always satisfies transitive condition, right? No other starts with 1. So we say that this pass transitive test. Now come to this. This ends with 2. Any other starts with 2? No. We say that this pass the transitive test. And this ends with 3. Any other starts with 3? No. So in that case, what we say, this element pass the transitive test. All the elements passes the transitive test. So in this case, we say that this relation is transitive. Now I taken one more relation. It is a subset of A cross A. So now I need to check this relation is transitive or not. Okay. Come to the first one. This ends with 2, correct? This ends with 2. Now you need to look that any other starts with 2. Yes, here it is there. It starts with 2. 1 comma 2, 2 comma 3. What is x comma z? X comma z is 1 comma 3. 1 comma 3 is there in this relation? Yes, 1 comma 3 is there in this relation. From this, you cannot say that it is transitive. We can say that just this order pair passes the transitive test. Like that, you need to check for every x comma y comma z in the relation. Okay. Now, come to second order pair. This ends with 3. Any other order pair is there which starts with 3? No other order pair starts with 3. So, we say that this order pair passes the transitive test. Now, come to this. This ends with 3. Is there any other order pair starts with 3? No. In this case, we say that this passes the transitive test. And come to this. See, this is like 1 comma 1, 2 comma 2, 3 comma 3. In such cases, what we say, this type of elements always passes the transitive test. If you want, you can check, but no need to check. See here, this ends with 1. Any other starts with 1. This starts with 1. This starts with 1. First, we'll check with this one. This is 1 comma 1. This ends with 1. This starts with 1. What is x comma z here? X comma z is 1 comma 2. 1 comma 2 is there here. Now you see here 1 comma 1, 1 comma 3. I hope you are understanding. 1 comma 1, 1 comma 3. What is x comma z? X comma z is 1 comma 3. 1 comma 3 is there here. So that's why I'll say that for such type of elements, which type of elements? X comma x, 1 comma 1, 2 comma 2, 3 comma 3, such type of elements, no need to check the transitive condition. This always passes the transitive condition. So this element passes the transitive test. So R5 is transitive. I hope you understand this transitive relation. What is transitive relation? How to check the transitive relation? Next, equivalence relation. What is equivalence relation? A relation R on A is said to be equivalence relation if it is reflexive. It must be reflexive relation and it must be symmetric relation which is reflexive, symmetric and transitive. If a relation is reflexive, symmetric and transitive, then we say that that relation is equivalence relation. For example, you see here this relation. What is set A here? Set A is 1, 2, 3. 1, 2, 3. this relation, you observe this relation is reflexive or not. As 1 is there in set A, 1 comma 1 is there in the relation. As 2 is there in set A, 2 comma 2 is there in the relation. As 3 is there in set A, 3 comma 3 is there in this relation. So this relation is reflexive. Now we know that this type of elements always passes symmetric test. What is symmetric test? Symmetric means x comma y belongs to R, means y comma x also must belongs to the relation, right? For 1 comma 1, reverse order also 1 comma 1. This type of elements always pass symmetric test. So this relation is symmetric also. As we discussed now, it is transitive. Yes, this relation is clearly transitive. So this relation is equivalence relation. Yes, this relation is equivalence relation because it is reflexive, symmetric and transitive. I hope you understand this class. Exercise number 1.1, question number 1. What they are asking in all these questions: determine whether each of the following relations are reflexive, symmetric, transitive. That means we'll take one relation first and then we'll check that relation is reflexive relation or symmetric relation or transitive relation. These things we'll check for each bit in this first question. They given R is a relation on set A. That means they given set A here. First point, you write that one. Yes, what is set A? Set A is 1, 2, 3, 4, like that up to 14. This is the given set. Second point is this relation is from where to where. You observe R is a relation in the set A. That means R is a relation on A. It means that R is a relation from A to A. This point also important. You write that point. Given that R is a relation on A. R is a relation on A. It means that R is a relation from A to A. Okay. Third point, given relation. You observe this is the given relation. You write that one. See, this is the given relation. In all these bits in the first question, these three steps you need to observe carefully. Okay. Now I need to check this relation is reflexive relation or symmetric relation or transitive relation. All those three things I need to check for this relation. Here, whatever the things we learned till now in this chapter, in all those examples, the relation is in roster method like 1 comma 1, 1 comma 2, 2 comma 3, something like that. If the relation is like this, then we can easily check the relation is reflexive or symmetric or transitive, right? But this relation they given in set builder form. Elements are represented with its property. So the point is you need to write this relation into roster method, then we can easily check the relation is reflexive or symmetric or transitive. Okay. To write this relation in roster method, you observe these order pairs. Here R is a relation on A. Na? As R is a relation on A, R is a subset of A cross A. So here the point is X is in set A. X must belongs to set A. Y also must belongs to set A. X we can write 1, 2, 3, 4 like that up to 14. Y also we can write 1, 2, 3, 4 like that up to 14. You cannot write Y as 3 by 2 because 3 by 2 is not in this set A. As R is a relation on A, these two elements must belongs to set A. Okay. And one more thing, these two elements must belongs to this set A, and one more thing is this order pair must satisfy this condition. Whatever xy values we'll choose from set A, that must satisfy this 3x minus y equal to 0. So what I'll do to do this further, this 3x minus y I write separately. See, they given in the question 3x minus y equal to 0. From that, what is y? Y equal to 3x. Now keep this point in your mind, y equal to 3x. I'll start writing this relation into roster method. You know that x is from set A. So I'll take first element of set A, that is 1. Okay. When x is 1, what is y? As x is 1, that x value you substitute in this y equal to 3x, right? Put x equal to 1 in this, what you will get? Y is 3 into 1. That means y is 3. That means when x is 1, listen carefully, when x is 1, y is 3. So the first order pair what we will get is 1 comma 3. You observe one thing, this is there in set A, 3 is also there in set A, and when I substitute 1 comma 3 in this equation, it must and should satisfy. See, x value 1, y value 3, substitute in this, 3 into 1 minus, in place of y you write 3. So left hand side is 3 minus 3, 0, 0 equal to 0, satisfying. So this order pair 1 comma 3 belongs to this relation. Actually, this relation is in set builder form. I am writing this relation into roster method. Roster method is what? Set of all elements are listed like this. 1 comma 3 is one element. Now I need to take second element in this relation. Here you know that this x is from set A. As already 1 is over, now you take 2. In place of x, now x is 2. In this, in place of x, you write 2. Then what you will get? Y equal to 3 into 2. 3 into 2 is 6. So second order pair is 2 comma 6. If you observe this 2 and 6 both are there in this set, and when I substitute this 2 comma 6 in this, it must and should satisfy. It satisfies because this we are getting from this only. So you put x equal to 2 and y equal to 6 in this. 3 into 2 minus 6 equal to 0. See, 6 minus 6, 0 equal to 0, satisfying. So order pair 2 comma 6 belongs to this relation. Similarly, you take x is third element, x is 3. Put x is 3. When you put x is 3 in this, what you will get? Y equal to 3 into 3, y equal to 9. So this order pair is 3 comma 9. Similarly, you take x is 4. Put x is 4 in this. 3 into 4 is 12, y is 12. So this is 4 comma 12. After 4, you take x is 5. 5 is there here. You take x is 5. When I substitute x is 5 in this, what I'll get? Y is 3 into 5, 15. So this order pair is 5 comma 15. But the problem is, to be this order pair will be in this relation when these two numbers must be in set A. Here 15 is there, 15. 15 is not in set A. So the order pair 5 comma 15 does not belongs this relation. It doesn't belongs this relation because the 15 is not in this set A. This says that as it is a relation on A, x must be in set A, y also must be in set A. Similarly, if I take x is 6, y will become 3 into 6, 18. As 18 is not in set A, this doesn't belongs to this. 8, you take 7, x is 7. When you put x is 7 here, y is 21. 21 is also not in this relation. So these things, whatever further order pairs we'll get, when I take x equal to 8, x equal to 9, whatever order pairs we'll get, those order pairs does not belongs to this relation. I hope you understand. So what happened? I written the given relation in roster method. You observe in this all order pairs are listed and separated by commas. In this set total 4 elements are there. Okay, now it is easy for us to check the relation is reflexive or symmetric or transitive. Now I'll check this relation is reflexive or not. What is reflexive relation? For every x in set A implies order pair x comma s, x must belongs to the relation. This is what we learn in second class reflexive relation definition. For every x in set A, order pair x comma x must belongs to the relation. Here, what is set A? Set A is like this. You need to check for every element in set A that respective order pair x comma 1, x comma x belongs to the relation or not. Now, I'll take 1. For 1, 1 comma 1 is there in this relation? No. As condition of reflexivity fails here, directly I can write here this relation is not reflexive, right? I'll write here. What is the reason? For 1 is there in set A implies the order pair 1 comma 1 does not belongs to the relation. Because of this reason, I can say that R is not reflexive. In this particular example, it is not compulsory you will write like this. You see, in this set, 2 is there. Order pair 2 comma 2 is also not there. So you can write like this also. 2 is there in set A implies 2 comma 2 does not belongs to the relation. Here 1 comma 1 does not belongs to relation. For 2 belongs to set A, 2 comma 2 does not belongs to relation. Therefore, this relation is not reflexive. Like that also you can write. See, when the relation is not reflexive, identifying and writing the answer is very easy. When the relation is reflexive, for example, here 1 is there in set A. If 1 comma 1 also present in this, based on that, we cannot declare it is reflexive because you need to check for every x in set A, order pair x comma x belongs to relation or not. For 1, 1 comma 1 is there or not. If 1 comma 1 is there, for 2, 2 comma 2 is there or not, we'll check. For 3, 3 comma 3 is there, like that we'll check. We need to check for every x in set A. We'll check for every x in set A. Oh, now I need to check this relation is symmetric relation or not. What is symmetric condition? Symmetric condition is for every order pair x comma y in the relation, y comma x also must belongs to this relation. This is what we discussed in the theory part, right? So for every, this is important, for every order pair x comma y in the relation, y comma x belongs to the relation or not, we will check. If this holds good for every order pair x comma y, then we say that this is symmetric. Okay, now this is the relation. You take one order pair in this. For example, here 1 comma 3. Yes, let 1 comma 3 from the relation. 1 comma 3 belongs to R. For respect to 1 comma 3, 3 comma 1 is there in the relation or not? You check. 3 comma 1 is there? No, it is not there. So we can say that this relation is not symmetric. One more point here. For 1 comma 3, you suppose 3 comma 1 is there in this relation. From that, can I say it is symmetric? No. You need to check for every order pair. In that case, we say that this element passed the symmetric test. Now we'll come to 2 comma 6. For 2 comma 6, 6 comma 2 is there in this relation? No. So we say it is not symmetric. But for first order pair x comma y comma x is not in this relation. For 1 comma 3, 3 comma 1 is not in this relation. When one element satisfies to fail symmetric condition, then we say that it is not symmetric. Here 1 comma 3 is there in this relation. That implies 3 comma 1 does not belongs to the relation. So we say that this relation is not symmetric. Okay, I checked this relation is not reflexive. I checked a symmetric condition. I came to know that this relation is not symmetric also. Now I need to check transitive condition. What is transitive condition? For every order pair x comma y belongs to R and y comma z belongs to R, then we'll look for x comma z is there in the relation or not. For every such order pair, if x comma z exists, then we say that relation is transitive. Now, what I'll do here, I'll come with this first order pair. You observe this ends with 3. Now, you look at any other order pair in this relation which starts with 3. Yes, here it is. This starts with 3, this ends with 3. That means we are able to find x comma y comma z. X comma y comma z we are able to find. So what I'll write here, let 1 comma 3 is there in this relation and we are able to find 3 comma 9 also. When such order pair exists, then only we look for x comma z. 1 comma 9 is there in this relation. 1 comma 9 is there in this relation. You look that 1 comma 9 is there in this relation. No, that means for x comma y and y comma z, x comma z does not belong to this relation. So we can say that this relation is not transitive. So what I can write from this, 1 comma 3, 3 comma 9. 1 comma 9 does not belong to this relation. Therefore, this relation is not transitive. So in this question, they are asking us to check reflexive symmetric transitivity of this relation. This relation is not reflexive. This relation is not symmetric. This relation is not transitive. We need to check that whether this relation is reflexive or symmetric or transitive. Okay, you observe in this question they are saying that relation R in the set of all natural numbers. So R is a relation on set of all natural numbers. So as I said in last problem, we need to observe 3 points. In that, first point is relation is on which set. In this question, relation is on set of natural numbers. So you know what are natural numbers, 1 2 3 4 like that. All counting numbers are natural numbers. Okay, and they are saying R is a relation on set n. So I'll write that also. R is a relation on n means R is a relation from natural numbers to natural numbers. Okay, and the relation they given like this, we'll write this also. You observe this relation. This is similar to last problem. Here this relation is given in set builder form. This relation contains order pairs, right? As this relation, as it is a relation on set of all natural numbers, x is a natural number, y is also a natural number. Both these elements must belongs to this set. Okay, and here you observe this order pair must satisfy these two conditions. You observe x is a natural number which is less than 4. X is a natural number and less than 4. That means x you can take 1, 2, 3. You cannot take 4 because they are saying x is strictly less than 4. So I'll write this relation into roster method so that I can easily check reflexive, symmetric, transitive condition. So here x is less than 4, they are saying I'll take x equal to 1. First point, 1 is a natural number, okay, and 1 is less than 4. I'll put this x value in this. Put x value 1 in this, what you will get? Y is 1 plus 5. 1 plus 5 is 6. So first order pair is 1 comma 6. What point you need to observe? The order pair 1 comma 6 belongs this relation. Why? Why? Because 1 is a natural number, 6 is a natural number, and this x is less than 4, and this order pair 1 comma 6 satisfies this condition. If you want, you can check. In place of x, you write 1. In place of y, you write 6. Y equal to 6 equal to 1 plus 5. Definitely it's satisfied, right? Okay. Now, as x is a natural number and less than 4, I'll take x is 2. You take x is 2. Put x is 2 in this. What you will get? 2 plus 5 is 7. So, this order pair is 2 comma 7. Now, as x is a natural number and x is less than 3, I can take x as 3. You take x as 3. Put x is 3 in this. 3 plus 5 is 8. So, this order pair is 3 comma 8. You cannot take x equal to 4 because they are saying that x is a natural number and x is less than 4. You cannot take x equal to 4 because x is less than 4. So, this relation is completed. They given this relation in set builder method. I written this relation in roster method. Roster method means all the elements are listed. It is more clear now what elements are there in this relation. Okay. Now you need to check this relation is reflexive or symmetric or transitive. It is very easy for this problem. How to check a reflexive condition? What is the definition of reflexive relation? For every x belongs to A implies order pair x comma x belongs to R. In this question, this A is natural numbers. That means for every x belongs to N, you need to check that order pair x comma x is there in the relation or not. Okay. First, I'll take 1x from this natural numbers. I'll take 1. Order pair 1 comma 1 is there in this relation? No. Order pair 1 comma 1 is not in this relation. So what I can say, for 1 belongs to natural numbers implies order pair 1 comma 1 does not belongs to the relation. From this, you can say that the relation R is not reflexive. Now, I'll check symmetric condition. What is symmetric definition? For every order pair x comma y, this is important. For every order pair x comma y comma x also there in the relation or not, you need to check. Okay. Here, this is the relation. I am checking this relation is symmetric or not. First, you take one order pair, 1 comma 6. Yes, 1 comma 6 is there in this. Let 1 comma 6 in the relation. For 1 comma 6, 6 comma 1 is present in this relation. No, 6 comma 1 does not belong to this relation. So, what I'll say, 6 comma 1 does not belong to this relation. That means this element fails to satisfy symmetric condition. So, we say that this relation is not symmetric. So, given relation is not reflexive and given relation is not symmetric. Now, I'll check transitive condition. In this problem, transitivity is the tricky one. Observe the definition first. For every x comma y belongs to R and y comma z belongs to R, we look that x comma z is there in the relation or not. This is transitive condition, correct? Okay. Now, if there doesn't exist such ordered pair, x comma y comma z doesn't exist in the relation, in that case, no need to check for x comma z. We say that that relation is transitive. You try to understand. If there exists an order pair x comma y comma z in the relation, then only we look for x comma z. If there doesn't exist x comma y comma z in the relation, then no need to check this condition and we say that that relation is transitive. Let's see this relation. You observe. Here you observe this order pair ends with 6. Now you look that any other order pair starts with 6 in this relation. There is no other order pair starts with 6 in this relation. So that means for this x comma y, there doesn't exist y comma z to check x comma z. In that case, we say that this element passed the transitive test. Okay. Now come to this order pair. This ends with 7. You look that any other order pair starts with 7 in this relation. No other order pair starts with 7 in this relation. That means for the order pair 2 comma 7, there doesn't exist any other order pair which starts with 7. That means for x comma y, there doesn't exist y comma z. So no need to check for x comma z. So in this case also, we say that this relation is, this element satisfies transitive condition. Now come to this third order pair. This ends with 8. Any other order pair starts with 8? No. So we say that this element passes the transitive test. So overall, we identified that there doesn't exist x comma y belongs to R and y comma z belongs to R in the relation. So there is no need to look for x comma z. I hope you are understanding. You observe this clearly. For every order pair in the given relation, there doesn't exist y comma z. That means x comma y comma z does not exist in this relation. In this case, we say that the given relation is transitive. I discussed so many examples in the beginning of explanation of definition of transitive with the help of examples, right? Here, if I explain again, it is lengthy. You please check that video once. Definition of transitive relation and examples. So when we are unable to find x comma y comma z in the relation, in that case we say that the relation R is transitive. So this relation is not reflexive, not symmetric, but it is transitive. See, they given one relation here. We need to check this relation is reflexive, symmetric, transitive. Okay, we need to check this relation satisfies which condition. You see, this is the given question. As usual, in this first question, for all the bits, first we'll write 3 steps. First one is relation is on which set. If you observe, this relation is on this set A. So I written set A. Second step is relation is on which set. They given that R is a relation in set A. They mention that R is a relation on A. That means that R is a relation from A to A. That means that R is a subset of A cross A. And main important thing is how the relation is defined. They define relation like this. R equal to order pair x comma y such that y is divisible by x. Okay. Before going to continue this further, you need to know about A cross A because all these order pairs are from A cross A. A cross A. A cross A contains what elements? You look here. A cross A. A is 1, 2, 3, 4, 5, 6 cross 1, 2, 3, 4, 5, 6. A cross A contains what elements? You tell 1, comma 1, 1, comma 2, 1, comma 3, 1, comma 4, 1, comma 5, 1, comma 6. I hope you are understanding. Take 1, you pair with all the elements of this, right? Similarly, next you take 2. What you will get? 2, comma 1, 2, comma 2, 2, comma 3, 2, comma 4, 2, comma 5, 2, comma 6. Next, take 3. Take 3. 3, comma 1, 3, comma 2, 3, comma 3, 3, comma 4. Like that, it is not a good idea to write A cross A 36 elements. So, but keep in your mind that what are there in A cross A. Okay, based on that, we are going to write this relation. Okay, now I'll write this relation in roster method. Actually, this is in set builder method. I list what elements are there in this relation. You know that all the elements, order pairs comes from A cross A. A cross A first element is what? A cross A first element is order pair 1, comma 1. I'll take 1, comma 1. Now I'll check that this 1, comma 1 is there in this relation or not. 1, comma 1 will be present in this relation when y is divisible by x. You see, this is x, this is y. Here y is 1. Y is divisible by x. Here 1 is divisible by 1. Yes, we know that 1 is divisible by 1. So order pair 1, comma 1 belongs this relation. Okay. In A cross A, first element is 1, comma 1. In A cross A, what is the second element? In A cross A, second element is 1, comma 2. In A cross A, second element is 1, comma 2. Now, is 1, comma 2 belongs this relation or not? See here, 2. Y means 2. Here, 2 is divisible by 1. You check that 2 is divisible by 1 or not. 1 in this 2 times. Remainder is 0. As we are getting remainder 0, we can say that 2 is divisible by 1. That means order pair 1, comma 2 is there in A cross A and order pair 1, comma 2 is satisfying this condition. So order pair 1, comma 2 belongs this relation. I hope you understand. In A cross A, next element is 1, comma 3. Now you take this 1, comma 3. 1, comma 3 belongs this relation. You check. In place of y, you write 3. Here 3 is there. 3 is divisible by, in place of x, you write 1. Is 3 is divisible by 1? You check. Is 3 is divisible by 1? Yes, 3 is divisible by 1. You can easily say that 3 is divisible by 1. Similarly, in A cross A, next element is 1, comma 4. 4 is divisible by 1. Similarly, 1, comma 5, 1, comma 6, 1, comma 7. Can we write 1, comma 7? No, you cannot write 1, comma 7 because in A cross A, related to 1, here you'll write like this now: 1 2 3 4 5 6. Last element is what? 1 comma 6 only. 1 comma 7 does not belongs to this relation. Now in A cross A, next element is what? Next element starts like this: 2 comma 1, 2 comma 2, 2 comma 3, 2 comma 4, 2 comma 5, 2 comma 6, like that. 2 comma 1, you take 2 comma 1. 2 comma 1 is there in A cross A. Now you need to check this 2 comma 1 is there in this relation or not. When 2 comma 1 belongs this relation, when y is divisible by x, that means 1 is divisible by 2. In place of y, you write 1. Is 1 is divisible by 2? Is 1 is divisible by 2? See, actually 1 is divisible by 2 means 1 by 2. 1 by 2 is not an integer. You are getting 0.5. You can easily say that 1 is not divisible by 2. That means order pair 2 comma 1 does not belongs to this relation. Next, after 2 comma 1, what element will be there in A cross A? That is 2 comma 2. 2 comma 2 is there in A cross A. Now we will check that 2 comma 2 satisfies this condition or not. In place of y 2, in place of x also 2, right? Is 2 is divisible by 2? Yes, 2 is divisible by 2. 2 by 2 is 1. It is an integer, right? Yes, 2 comma 2 belongs this relation. Now like that you need to check every element in A cross A. 2 comma 3. 2 comma 3 does not belongs this relation, because when we check for 2 comma 3, look here, 2 comma 3. 3 is not divisible by 2. 3 is not divisible by 2 because 3 is odd number. Next, after 2 comma 3, 2 comma 4. Is 4 is divisible by 2? Yes, 4 is divisible by 2. Next, 2 comma 4 is over. Next, 2 comma 5. Is 5 is divisible by 2? No. Next, 2 comma 6. I hope you are understanding. 3 comma 1? No. 3 comma 2? No. 3 comma 3? Yes. 3 comma 3 is there in A cross A. This 3 is divisible by 3. Okay. Next, 3 comma 4? No. 3 comma 5? No. 3 comma 6? Yes. Because 3 comma 6 is there in A cross A and 6 is divisible by x. Okay. Now 4 comma 1? No. 4 comma 2? No. 4 comma 3? No. 4 comma 4? Yes. 4 comma 4 is there in A cross A. 4 is divisible by 4. Okay. Next, 4 comma 5? No. 4 comma 6? No. Next, 5 comma 1? No. 5 comma 2? No. 5 comma 3? No. 5 comma 4? No. 5 comma 5? Yes. 5 comma 5 is there in A cross A. 5 is divisible by 5. Next, 5 comma 6? No. 6 comma 1? No. 6 comma 2? No. 6 comma 3? No. 6 comma 4? No. 6 comma 5? No. 6 comma 6? Yes. 6 comma 6 is the last order pair in A cross A and 6 is divisible by 6. Okay, right. Now I written this relation in roster method. It is not compulsory to write these elements because this is a bigger set. If you write it, you can easily check. Okay. Now I need to check that this relation is reflexive or symmetric or transitive. All those things I need to check. Okay. Reflexive. How to check reflexive? What is the definition of reflexive? For every x in set A, order pair x comma x is there in the relation or not? That we will check. Okay. Right. You take 1 in set A. For 1 in set A, 1 comma 1 is there in A cross A? Yes. For 2 in set A, 2 comma 2 is there in A cross A? Yes. For 3 in set A, 3 comma 3 is there in A cross A? Yes. For 4 in set A, 4 comma 4 is there in A cross A? Yes. For 5 in set A, 5 comma 5 is there in A cross A? Yes. For 6 in set A, 6 comma 6 is there in A cross A? Yes. So what happened here? For every x in set A, order pair x comma x is there in this relation. So I can say that this relation is reflexive. I hope you understand. So how you will write the answer? You need to write like this. For every x in set A implies order pair x comma x belongs to the relation. From this, we can say that the relation R is reflexive. The relation R is reflexive. I hope you understand this. Now we will check symmetric condition. What is symmetric definition? For every order pair x comma y in the relation, y comma x also must present in the relation. Okay. Now you know that. See, this is the relation. This relation I'll check for every order pair. 1 comma 1 is there. For this type of elements, 1 comma 1, 2 comma 2, 3 comma 3 always satisfy symmetric condition. Okay. Now you come to this 1 comma 2. For 1 comma 2, 2 comma 1 is there in this relation. You check. Is there anywhere 2 comma 1? 2 comma 1? No. That means for the order pair 1 comma 2, 1 comma 2 is there in the relation, but 2 comma 1 doesn't belongs this relation. So for the order pair 1 comma 2 is there in the relation, but the order pair 2 comma 1 does not belong to this relation. So we say that this relation R is not symmetric. I hope you understand. Now we'll check transitive condition. How to check transitive condition? For this problem, we can do the solution in two methods. One is verifying by taking every order pair x comma y comma z exist or not. For x comma y comma z, x comma z exist or not. That is one procedure. Another procedure is directly by taking this condition, we can write transitive. So we'll do that method instead of checking, because here so many order pairs are there. Checking like that, it takes so much of time. So let's see how I'll do this problem. I'll take there exists an order pair x comma y and y comma z in the relation. If I suppose x comma y is there in the relation, that from the relation it says that y is divisible by x. If I say x comma y is there in this relation, this says that y is divisible by x. So this tells you that y is divisible by x. And here y comma z belongs to this relation. This tells you that z is divisible by y. Z is divisible by y. Here you need to know few basic things. If y is divisible by x, suppose 4 is divisible by 2. If 4 is divisible by 2, 4 can be written as multiple of 2. 2 into 2. 2 into some integer. This is integer. Please try to understand. This is some integer. As y is divisible by x, what thing you need to know that y is multiple of x. I'll write here y into k1. Here k1 is what? K1 is an integer, right? And as we know z is divisible by y, z can be written as multiple of y into some integer. Okay. Now what I need to look that x comma z is there in the relation or not. When I can say x comma z is in the relation, when I say that z is divisible by x, when I can say z is divisible by x, if z can be written as multiple of x, x into some integer. If z can be written as x into some integer, then I can say that z is divisible by x. Okay, so what I'll do here, first I'll write this z is equal to, what is z? Z is y into k2. Z is y into k2. Now you observe this further. Here y is there now. That y can be written as x into k1. Okay, then this is x into k1 into k2. Here what is k1? K1 is an integer. What is k2? K2 is an integer. So what I can write here, x into, if I multiply these two integers, again I'll get an integer. So I'll write it as k3. What is k3? Where k3 is the integer that we'll get when we multiply k1 and k2. So what the point here you need to observe, here I got z as a multiple of x. Z can be written as multiple of x. This itself indicates that z is divisible by x. If z is divisible by x, then what I can write? I can write that x comma z belongs to this relation. When x comma y, when x comma z belongs to R, if z is divisible by x now. So what happened here? If such type of order pair exists, then we came to know that x comma z also belongs to this relation. Another method is also there. In the beginning of definition of transitive relation, I check a transitivity with the help of every element. Like that also you can check and you can say, you can write the answer. But this is a better way of writing the solution of transitive for this relation, right? So for x comma y belongs to R, y comma z belongs to R, I got that x comma z belongs to R, then I can conclude that therefore this relation R is transitive. Here we'll conclude. This is the first one we got, this is the second one we got, and this is the third one. So from this 1, 2, 3, we came to know that the relation R is reflexive and transitive but not symmetric. I'll write the same thing. The relation R is reflexive and transitive but not symmetric. So this is the conclusion we given, that this relation is reflexive and transitive but not symmetric. I hope you understand this solution. This relations and functions concept actually easy, but this for particular problems, when we do the problems, a little bit of confusion will arise in your mind. That confusion you can clear only with a good knowledge on theory part. And moreover, as slowly started doing problems like this, at particular point you will come to know that yes, this relations is easy. Now you observe this fourth bit. We need to check this relation is reflexive or symmetric or transitive. Before going to that, we'll write what are the 3 points we need to observe from this question. First point, this relation is on which set? This relation is on set Z. So I'll write Z. What are integers? You know, 0, plus 1, minus 1, plus 2, minus 2, plus 3, minus 3. These are the integers. Second point is R is a relation on what set? They given in the question that R is a relation on Z. R is a relation on Z. It means that R is a subset of Z cross Z. R is a relation on Z. It means that R is a subset of Z cross Z. Third one is how the relation is defined. Third point is relation is defined as order pair x comma y such that x minus y is an integer. So these 3 points in every problem of first question we are observing first and then writing. Okay, now we need to check this relation is reflexive or symmetric or transitive. As Z is an infinite set, Z cross Z is also infinite set. So writing this relation in roster method like 1 comma 1, 1 comma 2 like that, it's not a good idea. Actually, it is not possible to write actually because this is R is also infinite set here. You observe R is a relation given like this. Na? It tells you that X is what? X is an integer. What is Y? Y is also an integer. Which order pairs belongs this relation? You take two integers such that difference of them is an integer. For example, 2 is integer, 3 is integer. What is difference of them? 2 minus 3 is minus 1. Minus 1 is integer or not? Yes, minus 1 is an integer. Like that, if you observe, this R contains infinitely many ordered pairs, right? So best thing is generally by taking these points, we'll try to check reflexive symmetric transitive without writing this relation into roster method. Reflexive relation. We need to check this is reflexive or not. Okay. What is reflexive condition? For every x in Z, here Z is there na? For every x in Z, order pair x comma x is there in the relation or not. That we'll check. Okay. Here, when order pair x comma x belongs to the relation, if x minus x is an integer, x minus x is what? X minus x is 0. 0 is an integer? Yes, 0 is an integer, right? So here, for every x in integer, you take any integer, we can say that x minus x is 0. 0 is an integer. Whatever integer you take 2. 2 minus 2 is 0. You take minus 2. Minus 2 minus of minus 2. That is 2 plus, that is minus 2 plus 2. That is 0, right? You take any integer, integer minus same integer, x minus x is 0, right? As x minus x is an integer, from this I can say that x comma x belongs to relation. So what happened here? For every x in Z, order pair x comma x belongs to relation. So I can write that the relation R is reflexive. Now this relation R is symmetric or not. What is symmetric? For every order pair x comma y in the relation, if the order pair y comma x also belongs to relation, then we say that relation is symmetric. Now what I'll do, I'll take one order pair from this relation. You take x comma y in the relation R. If x comma y is there in the relation R, it indicates that as per the definition, if x comma y is in the relation, it indicates that x minus y is an integer. As I taken x comma y in the relation, I can say that x minus y is an integer. Okay, x minus y is integer. Suppose x minus y is 2. If 2 is integer, minus 2 is also integer. You suppose x minus y is minus 4. Okay. Then minus of minus 4, that is also an integer. What I am trying to say, if x minus y is integer, then minus of x minus y is also an integer. If x minus y is integer, minus of integer, suppose minus 4 is there. Minus 4 is an integer. Minus of minus 4 plus 4 plus 4 is an integer. Minus of x minus y is what? Minus of x minus y is y minus x. So here we got that y minus x is an integer. As per this relation, when I can say that y comma x belongs to this relation, when I can say y comma x belongs to this relation, if y minus x is an integer. So here what I got that y minus x is an integer. From this what I can say, I can say that the order pair y comma x belongs to the relation. So what happened here? For every x comma y belongs to R, y comma x also belongs to R. So I can conclude that the relation R is, therefore, the relation R is symmetric. How to check transitive relation? What is transitive relation? For every order pair x comma y belongs to R and y comma z belongs to R, we'll look for x comma z belongs to the relation or not. So first I'll take x comma y belongs to R and y comma z belongs to R. This tells you that x minus y is an integer. Y comma z belongs to R. This tells you that y minus z is an integer. I'll write the same. X minus y is an integer. Y minus z is also an integer. So here what I need to check? I need to check x comma z belongs to the relation or not. I need to check that x comma z is there in the relation or not. It means that when x comma z belongs to R, if x minus z is an integer, if x minus z is an integer, then I can say order pair x comma z belongs to the relation. You know, addition of two integers is again an integer. Here I know that x minus y is an integer, right? Now I'll add x minus y and y minus z, because y minus z is also an integer. You know, sum of two integers is again an integer. So here you see this minus y plus y will get cancelled. Then what you will get? You will get that x minus z is an integer. If x minus z is an integer, what I can write? I can write that order pair x comma z belongs to R. When you came to know that x minus z is an integer, I can say that the order pair x comma z belongs to R. That means what happened here? For every x comma y comma z in the relation, x comma z also exists in the relation. From this, I can write that this relation is transitive. So we came to know that this relation is reflexive. I'll take it as 1. And this relation is symmetric. I'll take it as a second point. And this relation is transitive. You take it as a third point. From 1, 2 and 3. What you can say? As this relation is reflexive, symmetric, transitive, I can say that R is equivalence relation. Therefore, the relation R is a equivalence relation. I hope you understand this first 4 bits in exercise number 1.1. Exercise number 1.1, question number 1. In that question number 1, we are doing this 5th bit from Relations and Functions chapter, class 12th mathematics. In this 5th bit, again another 5 bits are there. In this class, we are going to learn all these 5 bits. If you observe the question, what they given, R is a relation on set A. And what is set A? Set A is human beings in a town at a particular time. And relations are there, 5 relations are there. We need to check these relations are reflexive, are symmetric, are transitive. Those things we need to check. If you observe last 4 bits in first question, we mainly written 3 points. First one is relation is on which set. Here set is set of humans in a town. First I'll write that. What is A? Given set A is set of humans in a town at a particular time. Second one is relation is on which set. You see here R is a relation in the set A. They given that R is a relation on A. R is a relation on A means R is a relation from A to A. And finally, given relation. In A bit, the relation is given like this. Order pair x comma y such that x and y work at same place. Here, R is a relation on A. So, x is there in set A. That means x is a human in a town. What about y? Y is also human in a town. Which order pair belongs to this relation? That is important. Which order pair belongs to this relation? First point, x, y must be humans in a town at a particular time. They must be humans and x and y work at a same place. For example, I take in that x, y work at a different place. Suppose x and y work at different companies. In that case, this order pair x comma y does not belong to this relation. You need to understand which order pairs are there in this relation. To be a part of order pair in this relation, only when they work at same place and those two are from set A. Now, we will check a reflexive condition. What is reflexive definition? For every x in set A implies order pair x comma x is in the relation, then we say that that relation is reflexive relation. For every x in set A, I'll take one human being from this set. Let's see what happens. I take in for any x in set A, that means x is a human being. You observe this, x and x works at same place. X and x. These two x are different? No. Actually, x is a person in a town. Same person. Can I say that x and x works at same place? Yes, we can say that x and x obviously will be at the same place where x is working. X works there only. A simple thing, nothing is there. Actually, it's funny to think about it. X and x works at same place is true. For any x belongs to A, x and x work at same place. From this, we can write that the order pair x comma x belongs to the relation. So, we came to know that for any x belongs to A, order pair x comma x belongs to this relation. So, I can say that this relation is reflexive. Therefore, the relation R is a reflexive relation. Now I'll check this relation is symmetric or not. How to check symmetric condition? For every order pair x comma y in the relation, the order pair y comma x is also in the relation. Then we say that that relation is symmetric relation. First, we'll take one order pair from this relation. You take one order pair x comma y in the relation. If order pair x comma y is in this relation, it indicates that x and y work at same place. As order pair x comma y belongs to this relation, that indicates that x and y work at same place. As we take an x comma y in the relation R, you need to check that y comma x is there in the relation or not. When y comma x belongs to this relation, if y and x works at same place. If x and y works at same place, from that, can I say that y and x also works at same place? See, it's a simple thing. No need to think much about these things. X and y work at same place. Obviously, y and x also works at same place. Suppose two persons are there. A and B works at same place. Can I say that B and A also works at same place? Yes. If y and x works at same place, then what I can write? I can write that the order pair y comma x belongs to the relation. So what I got here, for every x comma y in the relation, y comma x also belongs to this relation. So I can write that this relation is symmetric. Therefore, the relation R is symmetric. Now we'll check a transitive condition. What is transitive condition? For every pair of order pair x comma y belongs to R and y comma z belongs to R. If such pair exists, then we'll look that x comma z is there in the relation or not. For such pair, if x comma z is there in the relation, then we say that that relation is transitive. First, you take x comma y belongs to R and y comma z belongs to R. You take such order pair in the relation. X comma y belongs to R, it indicates that x and y work at same place. As we written x comma y belongs to R, it indicates that x and y work at same place. As we taken y comma z belongs to R, it indicates that y and z works at same place. X and y works at same place. Y and Z also works at same place. You please observe. It indicates that suppose X and Y work at company A, works at same place, works at company A. Y and Z works at same place. As Y is working at A, Y and Z also works at A. This indicates that X and Z works at same place. This is very simple thing. How to explain this? It is easy. With common sense we can understand. If x and y work at same place, y and z also working at same place, that means here y is common in both. That means all these three are working at the same place. So I can say that x and z works at a same place. As x and z works at same place, from this I can write that the order pair x comma z belongs to the relation. So what happened here? For every x comma y, y comma z belongs to R, x comma z also belongs to R. Therefore, the relation R is transitive. So, if you observe this relation, x and y works at same place, this relation is reflexive, this relation is symmetric, this relation is transitive. What I'll do, this reflexive I'll take it as 1, this symmetric I'll take it as 2, this transitive I'll take it as 3. From 1, 2, 3, we can say that the given relation R is an equivalence relation. What is equivalence relation? If a relation is reflexive, symmetric, transitive, then we say that that relation is equivalence relation. I hope you understand the solution of this A bit. If you observe the B bit, actually A bit, B bit almost same. You observe A bit, they are saying that X and Y works at same place, and in this they are saying that X and Y live in the same locality. So this relation is also equivalence relation. Both are similar. Let's see the solution of this quickly. I'll quickly explain this B bit. As usual, total 3 points will be there in this type of problems. First one is set A. What is set A? Set of humans in a town at a particular time. R is a what? R is a relation on A. These things given in the question. And the relation is defined like this. R is a relation set of order pairs x comma y such that x and y live in the same locality. Last problem is x and y work at same place. Here x and y live in the same locality. Now reflexive relation. Let's see how to write the answer for this. You know what is reflexive definition? For any x belongs to A, order pair x comma x belongs to the relation, then we say that relation is reflexive. Here I taken one x in set A. That means x is a human in a town. Now if I say like this, x and x lives in the same locality. Suppose x is the same person. Where x is there, x will be there only. It's a simple common sense thing. X and x lives in the same locality. If I say like this, anything wrong in this statement? Where x is living there only. Yes, x and x live in same locality. We can say like that. So whatever I written here, that statement is true, right? So from this, if x and x live in the same locality, then the order pair x comma x belongs to the relation. So I written here order pair x belongs to this relation. Therefore, the relation is R is reflexive. I taken it as 1. Now I'll check this relation is symmetric or not. Symmetric. What is symmetric condition? If you take an order pair x comma y in the relation, y comma x also belongs to the relation, then we say that that relation is symmetric. Suppose I taken any for some order pair x comma y in the relation. When the order pair x comma y belongs to the relation, if x and y live in the same locality, right? Use your common sense. You know this point, x and y live in the same locality. If x and y live in the same locality, we can easily say that y and x also lives in the same locality. It's a common sense related thing. You can understand this easily. If x and y lives in same place, y and x also live in the same locality, right? So I can say that this statement is also true. As y and x lives in the same locality, from that I can write that the order pair y comma x belongs to the relation. So for every order pair x comma y belongs to R, y comma x also belongs to R. Therefore, we say that this relation is symmetric. Now I'll check transitive. For transitivity, we will take a pair of order pairs like this. X comma y belongs to R and y comma z belongs to R. If x comma y is there in the relation, that itself indicates x and y live in the same locality. Y comma z belongs to R. This indicates that y and z lives in the same locality. You observe in these two statements, y is common, right? That means suppose y is in a some location of A, right? Here y is some location of A. So x and y in location A, y and z also in location A. From this we can say that x and z are in the same location, right? From this we can say that x and z live in the same locality. This is common sense related. You can understand this easily. So as x and z lives in the same locality, I can say that the order pair x comma z belongs to the relation. So for every pair of such order pair x comma y comma z, x comma z also belongs to this relation. I'll say that this relation is transitive. So if you observe this relation is reflexive, this relation is symmetric, this relation is transitive. From 1 to 3, we can say that this relation is equivalence relation. I hope you understand the solution of this second bit. You observe this C bit. A is a set of humans in a town. R is a relation on A, and the relation is like this. Order pair x comma y such that x is exactly 7 centimeters taller than y. Now you need to check this relation is reflexive or symmetric or transitive. First, we will check reflexive condition. What is the definition of reflexive? For every x in set A implies order pair x comma x belongs to the relation. Then we say that that relation is reflexive. Here, I'll take one x from set A. For any x in set A. I taken one x from this set A. A contains all human beings. You observe this, what I written here. X is exactly 7 centimeters taller than x. X is one person. Here x is also same person. Is it possible that one person is exactly 7 centimeters taller than same person? Suppose you are a height of 5 feet. Can I say that you are exactly 7 centimeters taller than your height? Can I say like that? No, this is false. So x cannot be exactly 7 centimeters taller than x. When the order pair x comma x belongs to the relation, if x is exactly 7 centimeters taller than x, then only this order pair belongs to this relation. Here x cannot be exactly 7 centimeters taller than x. Na? This indicates that the order pair x comma x does not belong to this relation. Therefore, the relation R is not reflexive. This relation R is not reflexive. Now I'll check symmetric condition. What is the definition of symmetric? For any order pair x comma y, if we take in the relation order pair y comma x also present in the relation, then we say that relation is symmetric. I taken one order pair x comma y in the relation. If x comma y belongs to R, what it mean? If x comma y belongs to R, it indicates that x is exactly 7 centimeters taller than y. Suppose you observe here, this is x, this is y. Okay, you suppose that x is exactly 7 centimeters, x is exactly 7 centimeters taller than y. Is y is also exactly 7 centimeters taller than x? No. Actually, y is exactly 7 centimeters shorter than x. Okay. When we say y comma x belongs to the relation, when we say y comma x belongs to the relation, if y is exactly 7 centimeters taller than x, then only we say that y comma x belongs to R. As we came to know that x is exactly 7 centimeters taller than y cannot be exactly 7 centimeters taller than x. Moreover, if we speak correctly, y is exactly 7 centimeters taller than 7 centimeters shorter than x. Y cannot be exactly 7 centimeters taller than x. It is not possible. This is not possible. Y is exactly 7 centimeters tall shorter than x. Okay. From this, I can write that the order pair y comma x does not belong to the relation. So as per the definition, for every x comma y belongs to R, y comma x also belongs to R. Here y comma x does not belongs to R. So I can write that the relation R is not symmetric. So this relation is not symmetric. Now we'll check transitive condition. What is transitive condition? For any pair of order pair x comma y belongs to R and y comma z belongs to R, then we look that the order pair x comma z is there in the relation or not. If such order pair x comma y comma z exists and x comma z also belongs to R, then we say the relation is transitive. I'll take an order pair x comma y belongs to R and y comma z belongs to the relation. X comma y belongs to R. What it represents? X comma y belongs to R represents that x is exactly 7 centimeters taller than y. Y comma z belongs to R. What it represents? Y comma z belongs to R represents that y is exactly 7 centimeters taller than z. Here you need to observe few things. First you see x is exactly 7 centimeters taller than y. Suppose this is x. X is exactly 7 centimeters taller than y. Okay, and y is exactly 7 centimeters taller than z. What is the relation you will say about x and z? X is exactly 14 centimeters taller than z. You please try to understand. X is exactly, see this difference is there, na? This is 7. This difference is there, na? This is 7. 7 plus 7, 14. X is exactly 14 centimeters taller than z. That means x comma z belongs to the relation. When x comma z belongs to the relation, if x is exactly 7 centimeters, exactly, try to understand, they are saying x is exactly 7 centimeters taller than z, then only that order pair belongs to the relation. Here they are saying that x is exactly 14 centimeters taller than z. That means the order pair x comma z does not belong to the relation. The order pair x comma z does not belongs to the relation. So for this order pair x comma y belongs to R, y comma z belongs to R, we came to know that the order pair x comma z does not belongs to the relation. From this we can say that the relation R is not transitive. Therefore, given relation is not reflexive, it is not symmetric, it is not transitive. I hope you understand solution of this bit. These are bit easy only. With a little bit of common sense, you can understand this solution very easily. You observe next bit in this question. They are saying set A is set of all humans in a town, and they are saying R is relation on set A, and order pair x comma y says that x is wife of y. Actually, it is funny question. See, which order pair belongs this relation? If x is wife of y, then only that order pair belongs to this relation. Suppose x is brother of y. You suppose x is brother of y. As that order pair x comma y belongs to this relation? No. This relation contains order pairs in which x must be wife of y, right? Suppose y is wife of z. Then the order pair y comma z belongs to this relation? Yes, the order pair y comma z belongs to the relation. You need to understand what type of order pairs are there in this relation. Okay, now we need to check is this relation is reflexive or not. What is reflexive definition? For every x in set A implies the order pair x comma x is there in the relation, then we say that relation is reflexive. Okay, for any x in A, I take an x in set A, that means x is a human. Okay, when what to check? We need to check order pair x comma x belongs to the relation or not. When x comma x belongs to R, if I say x is wife of x, if x is wife of x, then the order pair x comma x belongs to the relation. Okay, you observe x is wife of x. How funny it is. X is wife of x. Is it possible? Is it possible that x is a wife of x? Any person is there? Is it possible that the person is wife of oneself? No, it's not possible. X cannot be a wife of x. This is not possible, right? So the order pair x comma x belongs to the relation or does not belong to the relation. If x is a wife of x, then only order pair x comma x belongs to the relation. Here x cannot be wife of x. It is not possible. So we will write that the order pair x comma x does not belongs to the relation. Therefore, the relation R is not reflexive. This relation is not reflexive. Now we'll check symmetric condition. What is symmetric? For every order pair x comma y in the relation, if y comma x also belongs to the relation, then we say that that relation is symmetric. First, I'll take one order pair in the relation. I taken one order pair in the relation. When the order pair x comma y belongs to R, what it indicates? It indicates that x is a wife of y. If x is a wife of y, then only the order pair x comma y belongs to R. As I taken one order pair in the relation, this indicates that x is wife of y. If you observe the funny part here, x is wife of y means x is female in general, correct? X is wife of y means x is female, y is male. Okay, now what you need to look? You need to look that y comma x belongs to R or not. When y comma x belongs to R, y is wife of x. If y is wife of x, then y comma x belongs to R. One person can be a wife of some person means y must be female, right? As here x is wife of y, we already know that x is wife of y. That means y is a male. Male person cannot be wife of some person. Male person can be husband. I hope you are understanding. I need to look for y comma x belongs to the relation or not. But y comma x cannot belong to this relation because as y is a male, y cannot be a wife of some person. So y cannot be a wife of x. From this what I can say? I can say that the order pair y comma x does not belong to the relation. Therefore, for an order pair x comma y in the relation, y comma x does not belong to the relation. Therefore, I can write that the relation R is not symmetric. This relation is not reflexive. This relation is not symmetric also. Now we'll check transitive condition. What is transitive condition? For any x comma y belongs to R and if y comma z belongs to R also exists, then for this pair of order pairs, we look that x comma z exists in the relation or not. Here important thing is, if x comma y comma z doesn't exist in the relation, in that case no need to look for x comma z. We directly say that that relation is transitive, that we already discussed in earlier problems. In the theory part also we discussed. If x comma y comma z exists, then we look for x comma z. If x comma y comma z doesn't exist, then we don't look for x comma z. We directly say the relation is transitive. Okay. First thing, I'll check that x comma y comma such type of things exist in the relation or not. We'll check. Here the order pair x comma y belongs to R itself indicates that x is a wife of y. The order pair y comma z belongs to R, it indicates that y is wife of z. Now it is important to check that this type of things will exist or not. Suppose x is wife of y. X is wife of y means x is female, y is male. Please observe this carefully. As y is male, is it possible that a male person is a wife of some person? This person may be anything. Here the question is, as y is male, is it possible that y is wife of? Y can be husband because y is a male person here. So what happened? For order pair x comma y comma z doesn't exist in the relation. You try to understand. If x comma y comma z exists, then only we look for x comma z. If x comma y comma z, such pair of order pair doesn't exist, in that case we say that that relation is transitive. So what is the conclusion we'll write? For the order pair x comma y in the relation R, there doesn't exist y comma z in the relation. If x comma y comma z exists, then only we look for x comma z. As for x comma y comma z does that type of things doesn't exist, in that case we say that the relation is transitive. I hope you understand. See, these things we discussed in the theory part while discussing definition of transitive relation with the help of examples. At that time I explained this more clearly. So this relation is not reflexive, not symmetric, but this relation is transitive. I hope you understand solution of this problem. Actually it's really easy. You may confuse in this, nothing to confuse, especially in transitive part. We discussed it more clearly about this. If x comma y comma z exists in the relation, then only we look for x comma z. Otherwise we say that that relation is transitive. I hope you understand this. You observe this E bit, it is similar to D bit. In this, 3 points you need to observe. Given set is set of humans in a town. They are saying that R is a relation on set A. And the relation is like this, which contains order pair x comma y. And when we say order pair x comma y belongs to R, if x is father of y, then only order pair x comma y belongs to R. Suppose x is wife of y. Suppose x is wife of y. In that case, can we say order pair belongs to this relation? No. If x is a father of y, then only x comma y belongs to the relation. Okay. Now I need to check this relation is reflexive or not. What is reflexive condition? For every x in set A, order pair x comma x is there in the relation or not. This we need to check. Okay. I taken one x in A. A contains all human beings. Here x is a human being. Is it when we say x comma x belongs to R? If x is a father of x is a father of x, then we say order pair x comma x belongs to this relation. Is it possible? How funny it is. One person can be father of himself? No, it's not possible. It is a common sense thing. You can easily understand that x cannot be father of x. If x is a father of x, then only the order pair x comma x belongs to this relation. As x is not a father of x, the order pair x comma x does not belong to the relation. As order pair x comma x does not belong to the relation, we can say that this relation is not reflexive. I hope you understand this. Now we'll check symmetric condition. What is symmetric condition? For any order pair x comma y belongs to R, y comma x also belongs to relation, then we say it is symmetric, right? Now I taken one order pair x comma y in the relation. What it mean? It means that x is a father of y. When I can say y comma x belongs to the relation, if y is father of x, then I can say the order pair y comma x belongs to this relation. Okay. If x is a father of y, here what you need to observe, if x is a father of y, means that x is a male, y can be male or female, then y is son of x or y is daughter of x. You try to understand. Y cannot be father of x. It is impossible. Y cannot be father of x. If y is father of x, then only y comma x belongs to R. As y cannot be father of x, we can say that the order pair y comma x does not belong to this relation. Therefore, this relation is not symmetric. Now, we'll check transitive condition. What is transitive condition? For every such pair x comma y comma z exists in the relation, then we look that x comma z is there in the relation or not. Okay. First, I taken x comma y comma z in the relation. X comma y belongs to R means x is a father of y. X is a father of y and y is a father of z. First, we'll check that x comma y comma z such pair exists or not. You suppose x is a male, y is also male. Just suppose such pair exists or doesn't exist. If x is male, y is male, x is a father of y. Yes, it is possible. As y is male, y can be father of some z. What I am trying to say, in this relation, there exists a pair of order pairs x comma y comma z. X comma y comma z, such type of pair will exist in the relation. That's what I am trying to say. If x is male, y is female, in that case, female cannot be father of z. You try to understand, right? But the point is, such pair exist in the relation or not? Yes, such pair exists. When x is male, y is male, then y can be father of z. If x is father of y is father of z, then what is the relation between x and z? X and z relation is x is a grandfather of z. You can easily understand these things, man. No need of any example for this. You can understand it easily. X is a grandfather of z. When x comma z in the relation, if x is a father of z, there is so much difference between grandfather and father, right? If x is a father of z, then only x comma z belongs to R. Here x is not a father of z, x is a grandfather of z. That means the order pair x comma z doesn't belong to the relation. Therefore, this relation is not transitive. This relation is not reflexive. This relation is not symmetric. This relation is not transitive. I hope you understand the solution of this E bit. So we done total 5 bits in first question, 5th bit. I hope you understand all these solutions. See, creating videos takes so much of time. If you drop a like for this video, it gives me more energy to do many videos like this. If you like this video, please drop a like and share this video with your friends. In case if you are not yet subscribed to my channel, subscribe now. This is question number 2 in exercise number 1.1 Relations and Functions chapter. You observe this question, what they are asking. Show that the relation R on the set of all real numbers. The relation is defined like this. R equal to order pair A comma B such that A is less than or equal to B square. This relation is neither reflexive nor symmetric nor transitive. That means we need to show that this is not reflexive, not symmetric, not transitive. This is one of the good example to understand reflexive relation, symmetric relation, transitive relation. As usual, in first problem, in every bit, we written 3 steps mainly from the question. In this problem also, I'll write those 3 steps. First point is, this relation is on what set? This relation is on set of all real numbers. They given R. This R indicates set of all real numbers. You know what are real numbers? Union of rational numbers and irrational numbers are known as real numbers. Or any number you can mark on the number line is known as a real number. And real numbers in interval form we'll write like this. Open interval minus infinity to plus infinity. You take any number in between minus infinity to plus infinity, it is known as a real number. And second point is, this relation is on which set? Given that the relation R on the set of all real numbers, they given that R is a relation on set of all real numbers. That means R is a relation from real numbers to real numbers. Third point is how the relation is defined. The relation is defined like this. Order pair A comma B says that A is less than or equal to B square. Here, understanding this relation is important. I'll check few examples which order pairs are there in this relation. Here, R is a relation on set of all real numbers. Na? So, this A must be a real number and B must be a real number. A and B both are real numbers and A less than or equal to B square. For example, I'll take one order pair 1 comma 1. Here 1 is a real number. 1 comma 1 belongs this relation or not. The order pair 1 comma 1 belongs this relation. First point satisfied, both are real number. Second point is 1 is less than or equal to 1 square. See 1 less than or equal to 1 square is 1, right? Now you see 1 is not less than 1. In this 1 is not less than 1 but 1 equal to 1. So if I ask this is true or false means this is true because less than or equal, any one condition satisfied, it's okay. 1 equal to 1, that means the order pair 1 comma 1 belongs to this relation. I hope you are understanding. Now my question is order pair 1 by 2 comma 1 by 2 belongs to this relation or not. First point, 1 by 2 is a real number, 1 by 2 is a real number. Okay. Second condition, 1 by 2 is less than or equal to 1 by 2 whole square. 1 by 2 whole square is 1 by 4. Is it true? 1 by 2 means 0.5 less than or equal to 1 by 4 means 0.25. Is it true? 0.5 is less than 0.25? No. Is 0.5 is equal to 0.25? No. So, this tells you that this set of 1 by 2 comma 1 by 2, 1 by 2 is a real number, 1 by 2 is a real number, but it is not satisfying this condition. So 1 by 2 comma 1 by 2 does not belongs this relation. I hope you are understanding, right? Suppose I will take 1 comma 2. Is 1 comma 2 belongs this relation or not? First point, 1 is a real number, 2 is a real number. Yes, correct. Now this order pair 1 comma 2 satisfying this condition, you need to check 1 less than or equal to 2 square. 2 square is 4. Is it true? Yes, 1 is less than 4. It is true. As this is true, what I can say? I can say that order pair 1 comma 2 belongs to the relation. Here, it is important that which order pairs are there in this relation. This R contains infinitely many elements, many order pairs, right? We cannot write all those order pairs here now in a roster method, right? So, you need to know how to check a particular order pair belongs to that relation or not. Okay. Now I need to check this relation is reflexive relation or symmetric. No. I need to show that this relation is not reflexive. This relation is not symmetric. This relation is not transitive. How to check reflexive condition? For any x belongs to R set of all real numbers, order pair x comma x is there in the relation. Then we say that relation is reflexive. Okay, for any x belongs to real number, order pair x comma x belongs to R. Then we say the relation is reflexive. In this example, we need to show that this relation is not reflexive. When you are trying to say this relation is not reflexive, best thing is find an example. I'll take 1 by 2. Is 1 by 2 is a real number? Yes, 1 by 2 is a real number. Now I'll check that is 1 by 2 is less than or equal to 1 by 2 whole square. 1 by 2 whole square is 1 by 4. You observe this 1 by 2 less than or equal to 1 by 4. Is this true or false? 1 by 2 is 0.5. 1 by 4 is 0.25 less than or equal to. See 0.5 is not less than 0.25. That condition fails. 0.5 not equal to 0.25. That condition also fails. That tells you that this is false. As this is false, I can write that 1 by 2 comma 1 by 2 does not belongs to the relation. Here I taken one element in the set of all real numbers. I checked this order pair x comma x type that is not in the relation. That means this element fails to satisfy reflexive condition. So I can say that this relation R is not reflexive. See, in this relations and functions, when the relation is not reflexive, when the relation is not symmetric, when the relation is not transitive, writing the answer very easy. We give a counter example like this. See, so and so element fails satisfying reflexive condition, that's why this relation is not reflexive. We'll say like that very easily. But when it is reflexive, you cannot give an example like this. When it is reflexive, then you need to check for every element in that relation, for every element in that particular set satisfying x comma x belongs to R or not. I hope you understand. This relation is not reflexive. Now I'll check is this relation is symmetric or not. In this question, we need to show that this relation is not symmetric, right? Okay, this is the relation we need to show that this relation is not symmetric. For that, I'll take one element x comma y in this relation. I'll take one element x comma y in the relation, and I'll try to prove that y comma x does not belong to the relation. Okay, so let me take one order pair in the relation. I'll take 1 comma 2 in the relation. Now you need to check 1 comma 2 is there in the relation or not. Here 1 is a real number, 2 is a real number. Okay, is this order pair satisfying this condition or not? 1 is less than or equal to 2 square. 2 square is 4. Is this true or false? Here 1 is less than 4. Yes, 1 is less than 4. This is true. That means the order pair 1 comma 2 belongs to relation. Now what I need to check? I need to check 2 comma 1 is there in the relation or not. I need to check this. When I'll say 2 comma 1 is there in this relation, if 2 is less than or equal to 1 square, that means 2 is less than or equal to 1. You check, is it true? Is 2 is less than 1? No. Is 2 equal to 1? No. So what happened here? 2 is less than or equal to 1 square. This is false. Is this true? Means it is false. As it is false, what I can say? I can say that the order pair 2 comma 1 does not belong to the relation. Here there exists 1 comma 2 in the relation, but 2 comma 1 doesn't belong to the relation. It fails. The order pair 1 comma 2 fails to satisfy symmetric condition. I can say that this relation is not symmetric. Here one important point is finding an example like this. It is not necessary you also take 1 by 2 and you prove like that. You can take one more order pair which is in the relation x comma y such that y comma x does not belong to the relation. You can find such example. It's not compulsory you by heart this and you write the same order pair. You can find so many examples like this. So finding such type of examples is little difficult when you try the problem your own. Okay. Now transitive. In this we need to show that this relation is not transitive. So as this relation is not transitive, I need to find a pair of order pairs x comma y belongs to R and y comma z belongs to R, and I need to prove that x comma z does not belong to the relation. If I can find an example which is satisfying this condition, then I can easily say that this relation is not transitive. Okay, I'll take one example like this. I'll take 10 comma 4. I'll just check that then 10 comma 4 is there in this relation or not. First point, 10 is a real number, 4 is a real number. Second point, you need to check that a is less than or equal to b square. Here 4 square is 16. Is it true? 10 is less than 16. Yes, it is true. As it is true, 10 comma 4 belongs to this relation. Yes, correct. Now I am finding pair of order pairs like x comma y. Now I need to find y comma z. Y is already fixed here. Y is 4. I'll take 4 comma 2. Now I'll check this 4 comma 2 is there in the relation R or not. First point, both are real numbers. Second point, a less than or equal to b square. 2 square is 4. Is the statement is true? 4 is not less than 4, but 4 is equal to 4. Yes, equality condition is satisfying now. So this is true. Okay, so what happened? I am able to find x comma y, y comma z in the relation. Now I need to look that x comma z is there in the relation or not. What is x comma z? 10 comma 2. The order pair 10 comma 2 is there in the relation or not, that I need to check. Okay, order pair 10 comma 2. 10 is a real number, 2 is a real number. Now is this satisfies that condition a less than or equal to b square? 10 less than or equal to 2 square is 4. Is it true? 10 is less than 4? No. Is 10 equal to 4? No. So from that we can easily say that 10 comma 2 does not belong to the relation. Yes, from this we can say that 10 comma 2 does not belong to the relation because it fails to satisfy that condition a less than or equal to b square. Right? So what happened? I am able to find x comma y, y comma z in the relation such that x comma z is not in the relation. So I can write from this the relation R is not transitive. Therefore, this relation is not reflexive, not symmetric, not transitive. I'll name these things. This is 1, not reflexive. This is 2, not symmetric. This is 3, not transitive. From 1 to 3, I can say that R is neither reflexive nor symmetric nor transitive. I hope you understand this solution. You observe this question number 3. This is easy question compared to last question. Check whether the relation R on this set. The relation is defined like this. We need to check this relation is reflexive or symmetric or transitive. We need to check these things. As usual, what we are doing in question number 1, question number 2, those 3 steps we'll write first. First step, this relation is on which set? You see here, they given set, they didn't name this set. We'll name the set. I'll name it as A. The set A is 1, 2, 3, 4, 5, 6. Okay. And second point is relation is on which set? Relation R is on this set. That means R is a relation on A. This is second step. Third step, how the relation is defined. The relation is defined like this. It is a ordered pair A comma B such that B equal to A plus 1. Here you need to understand few things. Which order pair is there in the relation R? As R is a relation on A, this element A must belongs to set A, this element B also must belongs to set A, and this order pair must satisfy this condition B equal to A plus 1. So I'll write this relation in roster method so that we can easily identify this relation is reflexive or symmetric or transitive. As A must belongs to set A, I'll take 1 in place of A. Okay, for A equal to 1, you put A equal to 1 here, what you will get? B is 2, right? So the order pair 1 comma 2 belongs this relation. First point is 1, 2 both are there in this set, and this order pair 1 comma 2, when I substitute in this, it will satisfy. In place of A you write 1, in place of B you write 2. You see here, it satisfies. Now I'll write the next order pair. Here first element will be from set A. 1 is already over here, so I'll take A as 2. If I take A as 2, put A 2 here, what you will get? B is 2 plus 1, right? So B is 3. So order pair 2 comma 3. 2 is there in this set and 3 is also there in this set, and the order pair 2 comma 3 satisfies this condition. Now I'll write the third order pair. As A is there in set A, as 1, 2 already completed, I'll take 3. Put A 3 here, B is 4. So the order pair 3 comma 4 belongs to relation. Similarly, put A is 4. When you put A is 4, B is 5. Put A is 5. When A is 5, B is 6. We can take A is 6 also. If you take A is 6, put A is 6 here. 6 plus 1 is 7. You will get B is 7 when you put A is 6. But A, B both must belongs this relation. As 7 is not in this relation, the order pair 6 comma 7 does not belongs to this relation. I hope you are understanding. In place of A, if I take 6, B will become 7. So 6 comma 7 does not belongs to this relation. So finally, I written given relation in roster method. Actually, this is in set builder method. Now we written it into roster method. Now it is easy for us to check reflexive, symmetric, transitive. How to check reflexive condition? For any x belongs to set A implies order pair x comma x belongs to relation, then we say that relation is reflexive relation. Here I'll take one element from set A. Suppose 1 is there in set A. Yes, 1 is there in set A. Order pair 1 comma 1 is there in this relation? No. Here we can conclude that the relation is not reflexive. For 1 belongs to set A implies order pair 1 comma 1 does not belongs to relation. Therefore, I can say that the relation R is not reflexive. Now I'll check symmetric condition. What is symmetric condition? For every order pair x comma y in the relation, if y comma x also present in the relation, in that case we say that the relation is symmetric. Here this is the relation. Here 1 comma 2 is there in the relation. For 1 comma 2, 2 comma 1 is there in this relation? No. So here we can conclude that this relation is not symmetric. For 1 comma 2 is there in the relation. For 1 comma 2, 2 comma 1 does not belongs to relation. So I can say that this relation R is not symmetric. So this relation is not reflexive, not symmetric. Now I'll check transitive condition. How to check transitive condition? For every pair x comma y belongs to R and y comma z belongs to R. For every such pair x comma y comma z, if x comma z is also present in the relation, then we say the relation is transitive. Now you observe here this ends with 2. You look, any other starts with 2. Yes, here this is there, it starts with 2. That means there exists x comma y comma z. Look here, x comma y comma z exists. X comma y comma z. What is x comma z? X comma z is order pair 1 comma 3. order pair 1 comma 3 is there in this relation? No. So we can conclude here this relation is not transitive. There exists x comma y and y comma z in this relation. Now we look that x comma z, that means 1 comma 3 is there in the relation or not. You can check 1 comma 3 is not in the relation. 1 comma 3 does not belong to this relation. Therefore, the relation R is not transitive. So, given relation is neither reflexive nor symmetric nor transitive. When we are able to write given relation like this in roster form, in those cases, most of the time checking reflexive, symmetric, transitive is very easy. I hope you understand this solution. This is question number 4. You observe what they are asking in this question. Show that the relation R, which is defined on real numbers, and the relation is defined like this. This relation is reflexive, transitive, but not symmetric. We need to prove that. As usual, for all the 3 problems what we done till now in this exercise, we written 3 points in the beginning. I'll write those 3 points here. You observe they given this relation on set of all real numbers. So first I written what is given set? Given set is set of all real numbers. You know what are real numbers. Any number in between minus infinity to plus infinity are known as real numbers. Okay. And second point is the relation R in R. That means R is a relation on set of all real numbers. They mention that R is a relation on set of all real numbers. And third one is how the relation is defined. You see, the relation is defined as order pair A comma B such that A is less than or equal to B. First thing, to understand this solution very clearly, you need to know which order pair is there in this relation. As this relation is on set of all real numbers, A is a real number, B is a real number, and this order pair must satisfy this condition. For example, if I take 1 comma 2, is 1 comma 2 is there in this relation? For that, you see here 1 is a real number, 2 is a real number. You check that 1 is less than or equal to 2. Is this is true or false? Yes, 1 is less than 2. It is true. As it is true, the order pair 1 comma 2 belongs to this relation. Similarly, if I take 10 comma 4, 10 comma 4 is there in this relation or not? How to check? First point, 10 is a real number, 4 is a real number. Second point, you need to check the order pair 10 comma 4 satisfies this condition or not. 10 is less than or equal to 4. You observe, is 10 is less than 4? No, 10 is not less than 4. Is 10 is equal to 4? No, 10 is not equal to 4. So we can say that this order pair does not belong to the relation, right? Now you know what type of order pairs are there in this relation. Now we need to show that this relation is reflexive. We need to show this relation is reflexive. When it is reflexive, you have to write the answer carefully. One main thing that many students confuses is writing the solution of every problem. Here, from problem to problem, solution will vary little bit. Here, how to write this relation is reflexive relation. What is reflexive relation? For any x in set A implies order pair x comma x belongs to relation, then we say that relation is reflexive relation. Here, in place of A, they given real numbers. So what I'll do, I'll take a real number A. I suppose A is a real number. I taken one real number A. Now, order pair A comma A belongs this relation or not? First point, A is a real number, A is a real number. When the order pair A comma A belongs this relation, if it satisfies this condition, is A is less than or equal to A? A cannot be less than A. First condition is failed. Is A equal to A? Yes, second condition is satisfying. A equal to A. From that, I can say that this inequality is true. As this inequality is true, order pair A comma A belongs to the relation. I hope you understand. If I take any real number A, you know that A is less than or equal to A. This is true. As A is a real number and order pair A comma A satisfying this condition, from this I can write that the order pair A comma A belongs to the relation. From this, I can say that the relation R is reflexive. See, some students, they'll write the answer like this. 1 is a real number, 1 comma 1 belongs to relation. That's why this relation is reflexive. No, you cannot use such type of example when it is reflexive. You can give counter example when you can give counter example when it is not reflexive. So I proved that this relation is reflexive. Now I'll check symmetric. How to check symmetric condition? You see, in this they are asking show that it is not symmetric. When it is not symmetric, it is enough to give a counter example. Symmetric means what? for every x comma y in the relation, if y comma x also present in the relation, then we say that relation is symmetric, right? Here they are asking us to show not symmetric. So I'll give a counter example. I'll take one order pair 1 comma 2 in the relation. Is this order pair is there in this relation? First point, 1 is a real number, 2 is a real number. And is 1 is less than or equal to 2? Is this order pair satisfying this condition? That I need to check. Is 1 is less than or equal to 2? Yes, 1 is less than 2. That means order pair 1 comma 2 belongs to this relation. From this, now I need to check that the order pair 2 comma 1 is there in the relation or not. First point, 2 is a real number, 1 is a real number. This order pair satisfying this condition, you check 2 is less than or equal to 1. Is 2 is less than 1? No. Is 2 is equal to 1? No. So this order pair 2 comma 1 does not belongs to this relation, right? So we identified that for order pair 1 comma 2 in the relation, 2 comma 1 doesn't belongs to this relation. So we can write that this relation R is not symmetric. One important point you need to keep in your mind, when it is reflexive, you cannot give example type, like 1 is a real number, 1 comma 1 belongs to, like that you cannot write. When it is not reflexive, then you can give counter example. You see here, when it is not symmetric, we just given a counter example, right? If it is symmetric, then you cannot give examples like this. If it is symmetric, then you cannot give examples like this. As it is not symmetric, I given a counter example. I'll check transitivity. Is this relation is transitive or not? What is transitive relation? You take x comma y in the relation. You take x comma y and y comma z in the relation. If such order pair exists, then we look that x comma z is there in the relation or not. If x comma z is there in that relation, then we say that that relation is transitive. Okay. Now I'll take a comma b in the relation and b comma c. Such type of order pairs exists in this relation. When the order pair a comma b belongs to R, if I take an a comma b belongs to R, it indicates that a is less than or equal to b as per this relation. So as a comma b belongs to R, from this we can write a is less than or equal to b. And you see, the order pair b comma c belongs to R, from this we can write that b is less than or equal to c. Here you know that a is less than or equal to b and b is less than or equal to c. So what I can write here, I can write like this: a is less than or equal to b, b is less than or equal to c. From this, what you can conclude? You can conclude that easily a is less than or equal to c. Now the point is, I need to check a comma c is there in this relation or not. See, a is a real number, c is a real number. As a is less than or equal to c, look here, a, c, both are real numbers, and I came to know that a is less than or equal to c. So what I can say? I can say that the order pair a comma c belongs to this relation. As we got this, from this I can write that the order pair a comma c belongs to the relation. So therefore, the relation R is transitive. This relation is transitive. And you observe this relation is reflexive. This relation is not symmetric. This relation is transitive. We'll name here, this is 1, this is 2, and this is 3. From 1 to 3, what we can say? We can say that R is reflexive and transitive, but not symmetric. I hope you understand solution for this question. If you like this video, please drop a like. Share this video with your friends. In case if you are not yet subscribed to this channel, subscribe now. You observe this question. In this question, what they are asking? Check whether the given relation is reflexive, symmetric, transitive. In these problems, we'll observe mainly 3 points. First, I'll write those 3 points. First point, this relation is defined on which set? You observe here, they given R. This is set of all real numbers. So, this relation is defined on real numbers. I written R here. This R indicates set of all real numbers. And this relation R is in R. That means R is a relation in R means R is a relation on R. It means that R is a relation from R to R. How the relation is defined? You observe, this is important. The relation is defined like this. It contains an order pair a comma b such that a is less than or equal to bq. Here you need to understand which order pairs are there in this relation. Here, as R is a relation on set of all real numbers, a, b both must be real numbers. Okay, and the order pair a comma b must satisfy this condition, a less than or equal to bq. I'll take few examples here to understand this. For example, 1 comma 2. Is this order pair is there in this relation or not? First point, 1 is a real number. Second point, 2 is a real number. Yes, both are real numbers. Correct. Second point, is this order pair satisfying this condition? In place of A, you write 1. In place of B, you write 2. 2 cube means 8. 1 is less than or equal to 8. Is it true? Yes, 1 is less than 8. Yes, this is true. As this is true, I can say that the order pair 1, 2 belongs to this relation. I hope you are understanding. If I take 3, 3, the order pair 3, 3 is there in this relation or not? How to check? First condition, these two must be real numbers. Second condition, this order pair must satisfy this condition. You write here 3 is less than or equal to 3 cube. 3 cube is 27. Is 3 is less than 27? Yes, it is true. So what I can say from this? I can say that the order pair 3, 3 belongs to the relation. Like that, you need to know which order pair is there in this relation. Now you know what type of order pairs are there in this relation. Now we are going to check this relation is reflexive or symmetric or transitive. First, I need to check this relation is reflexive or not. What is reflexive? For every x in a set of all real numbers implies order pair x comma x is there in the relation, then we say that relation is reflexive relation. Here, when it is not reflexive, giving counter example is the easiest thing, right? Here what I'll do, I'll take one real number such that x comma x does not belongs to the relation, so that I can say that the relation is not reflexive. Here I'll try to find one example which is not satisfying this condition. I'll take 1 by 2. 1 by 2 is a real number? Yes, 1 by 2 is a real number. Now I'll check that order pair 1 by 2 comma 1 by 2 is there in this relation or not. I'll check this order pair is there in this relation or not. First point, 1 by 2 is a real number. Yes, 1 by 2 is a real number. Now, is this order pair satisfying this condition or not? You substitute, in place of A you write 1 by 2. In place of B also you write 1 by 2. What you will get? 1 by 2 is less than or equal to 1 by 2 whole cube. 1 by 2 whole cube is 1 by 8. 1 by 2 means you know it is 0.5, less than or equal to 1 by 8 means 0.12. Here 0.5 means 0.50. Now you observe, is it is true or false? 0.50 is less than 0.12? No. Is 0.50 equal to 0.12? No. So clearly we can say that the order pair 1 by 2 comma 1 by 2 does not belong to the relation. I hope you understand. Actually, for any x belongs to real numbers, I need to show that x comma x belongs to R. Then only I can say it is reflexive. But here I identified one real number which is failed to satisfy this condition. So I can write that this relation is not reflexive. How to check symmetric condition? You take one order pair. For any order pair x comma y in the relation, if order pair y comma x also belongs to the relation, then we say that that relation is symmetric. Here this relation is not symmetric. So I'll try to prove that this relation is not symmetric with the help of an example. Here it is not easy. You need to check, you need to take so many examples. You need to check. Here I am writing it directly, but when you try this your own first time, it is not so easy to find examples, right? However, for symmetric it is okay. I'll take one order pair in the relation 1 comma 2 in the relation. Now the point is this order pair 1 comma 2 is there in this relation? First point, 1 is a real number, 2 is a real number. Substitute this order pair in this. In place of A you write 1, in place of B you write 2. 2 cube, 2 cube is 8. 1 is less than or equal to 8. Yes, 1 is less than 8. This is true. So I can easily say that the order pair 1 comma 2 is there in the given relation. Now I'll check that the order pair 2 comma 1 is there in this relation or not. When I can say the order pair 2 comma 1 in this relation, first point 2 is a real number, 1 is a real number, because this is a relation on set of all real numbers. Now I'll substitute 2 comma 1 in this. Substitute, in place of A you write 2, in place of B you write 1. 1 cube is 1 only. You observe, is this is true or false? 2 is less than 1. 2 is less than 1? No. 2 is equal to 1? No. So we can easily say that the order pair 2 comma 1 does not belongs to the relation. 1 comma 2 belongs to R, but 2 comma 1 does not belongs to relation, as this element fails to satisfy a symmetric condition. I'll say that this relation is not symmetric. Here finding such type of examples is the task to you when you try the problems your own. How to check the transitive condition? First, I'll take a pair of order pairs like this. X comma y belongs to R and y comma z belongs to R. Later, I'll check that order pair x comma z belongs to the relation or not. If order pair x comma z belongs to the relation, then I say that that relation is transitive. You observe, I need to find a pair of order pairs. I'll take like this, 10 comma 4. You need to check this order pair 10 comma 4 is there in this relation or not. 10 is a real number, 4 is a real number. Yes, this order pair 10 comma 4 satisfies this condition. In place of a, you write 10 less than or equal to, in place of b, you write 4. 4 cube, 64. Yes, so 10 is less than 64. Clearly, the order pair 10 comma 4 belongs to the relation. Now, I'll take one more, like this ends with 4 na? So whatever I'll take, it must starts with 4. I'll take 4 comma 2. 4 comma 2 belongs to the relation. Now you check 4 comma 2 is there in this relation or not. First thing, 4 is a real number, 2 is a real number. This order pair 4 comma 2 satisfies this condition. In place of a, you write 4. In place of b, you write 2. 2 cube is 8. Is 4 is less than or equal to 8? Yes, 4 is less than 8. So this is true. So the order pair 4 comma 2 also belongs to relation. So I identified there is a pair such that x comma y comma z. See, x comma y comma z. I identified a pair. I need to check 10 comma 2 is there in this or not. 10 is a real number, 2 is a real number. Now this order pair you substitute in this. In place of a, you write 10. In place of b, you write 2. 2 cube is 8. Is 10 is less than 8? No. Is 10 equal to 8? No. So this is false. So from this we identified that the order pair 10 comma 2 does not belong to the relation. So what happened? This failed to satisfy transitive condition. Therefore, I'll write that this relation R is not transitive. Therefore, the given relation is neither reflexive nor symmetric nor transitive. Now, let's see one more question in this exercise number 1.1. Show that this relation R on this set, and the relation is defined like this, is symmetric. This relation is symmetric but neither reflexive nor transitive. That we need to show. Okay, as usual, first we'll write first 3 points. This relation is given on this set. Na? They didn't name this set. I'll name this set as A. Let given set as A, and they given that R is a relation on A, and the relation defined like this: order pair 1 comma 2, 2 comma 1. Okay, now I need to prove that this relation is neither reflexive nor transitive but symmetric. Okay, one by one we will check order wise. First we will check that reflexive condition. What is reflexive? For every x in set A implies order pair x comma x belongs to the relation, then I say that that relation is reflexive. For every x in A, here this is 1 is there in set A, na? You look, 1 comma 1 is there in this relation? No. So what I'll write here, for 1 belongs to set A implies the order pair 1 comma 1 does not belongs to relation. That implies the relation R is not reflexive. The relation R is not reflexive. Now I'll check symmetric condition. What is symmetric definition? For every order pair x comma y in the relation, if order pair y comma x also is there in the relation, then we say that relation is symmetric. Now you take here the order pair 1 comma 2 is there in the relation. For order pair 1 comma 2, reverse order like y comma x means 2 comma 1. You check 2 comma 1 is there in this relation. Yes, here it is, 2 comma 1 is there. Okay. For order pair 2 comma 1, 1 comma 2 is there. Yes, here it is. That means what happened? For every x comma y in the relation implies y comma x also belongs to the relation. Therefore, the relation R is symmetric. You observe how I written the answer. I written the answer in the form of definition. Here you cannot write like this. 1 comma 2 belongs to R implies 2 comma 1 belongs to R. That implies this relation is symmetric. If you say like that, that is wrong. You need to write every order pair in the relation x comma y comma x also present in this relation. Therefore, this relation is symmetric. So many students confuse in this. When it is not reflexive, you can give example like this. When it is reflexive, then you cannot give example, counter example. Okay, now we'll check transitive condition. See, for a transitive condition, if you observe, they are asking us to show that this is not transitive. So not transitive means you try to find x comma y comma z in the relation such that x comma z does not belong to the relation. You look here, this ends with 2, this starts with 2, right? So there is a pair like x comma y comma z. So here I'll write let 1 comma 2 is there in the relation and 2 comma 1 is also there in the relation. That means there exists a pair which satisfying the condition x comma y comma z. Look for x comma z. What is x comma z? 1 comma 1. You observe the order pair 1 comma 1 is there in the relation. No, 1 comma 1 does not belong to the relation. That means this pair fails to satisfy transitive condition. Therefore, R is not transitive. So, this relation is not reflexive. I'll take it as 1. This relation is symmetric. I'll take it as 2. This relation is not transitive. I'll take it as 3. From 1, 2 and 3, we can say that R is symmetric, but it is neither reflexive nor transitive. I hope you understand solution of this problem. If you like this video, please drop a like. Share this video with your friends. In case if you are not yet subscribed to my channel, subscribe now. This is the question from exercise number 1.1 Relations and Functions chapter, class 12 mathematics. You observe what they are asking. Show that the relation R, they given one relation R, that relation is an equivalence relation. First we will try to understand what is this relation. Till now, whatever the 6 problems we did in this exercise, in all 6 problems we written 3 points in the beginning. Here also we will observe. First thing, this relation is defined on what set? They named that set as A here. A is what? All books in a library. They given A as set of all books in a library. Second point is relation is defined on which set? Relation is defined on A. This is a relation on A. And how the relation is defined? They given it is a relation which contains order pairs. Here X is from set A. That means X is a book. Y is also book. And X and Y have same number of pages. Suppose A is a book which is having 500 pages. B is a book which is having 300 pages. Now my question is, this order pair A comma B belongs this relation? No. Which order pair belongs this relation? The books which are having same number of pages. Suppose this book is also having 500 pages. Now both the books are having 500 pages. In that case, we say that the order pair A comma B belongs to R. Now we need to show that this relation is equivalence relation. Equivalence relation means we need to show that it is reflexive, it is symmetric, it is transitive. First, we will check reflexive condition. What is reflexive condition? For any x belongs to A implies order pair x comma x belongs to the relation, then we say that relation is reflexive. So I'll take one book from set A. I suppose X is the book I taken from set A. Observe here I written one statement. X and X have same number of pages. X is a book, same book. Both are same books. When both are same books, obviously they will have same number of pages. What is the confusion in this? I hope you are understanding. Is there anything wrong in this statement? X and X have same number of pages. Nothing wrong in this. So when the order pair x comma y belongs to R, if x and y have same number of pages, if x and x have same number of pages, then what we say? We say that the order pair x comma x belongs to the relation. From this, I can say that the order pair x comma x belongs to the relation. Therefore, the relation R is reflexive. To check symmetric, for every order pair x comma y in the relation, order pair y comma x also belongs to the relation, then we say that that relation is symmetric. So I will take one order pair x comma y in the relation. Order pair x comma y is there in the relation. What it mean? It means that x and y have same number of pages. X and y have same number of pages. Can I say that y and x also have same number of pages? Obviously, if A, B are two books having same number of pages, then B and A also will have same number of pages. As y and x have same number of pages we got, from this what I can write? I can write that the order pair y comma x belongs to the relation. For every order pair x comma y comma x also belongs to this relation. From this I can write that this relation R is symmetric. To check transitive, first we will take x comma y in the relation and y comma z also present in the relation. Then we look that x comma z is present in the relation or not. To take x comma y comma z in the relation. Order pair x comma y belongs to the relation. What it means? It means that x and y have same number of pages. You observe here y comma z also belongs to relation. What it means? It means that y and z have same number of pages. You observe x and y have same number of pages. Suppose both are having 50 pages, I'll suppose. Here what is there? Y and Z have same number of pages. In this we came to know that Y is having 50 pages. So here Y is having 50 pages, Z is also having 60 pages. So X is having 50 pages, Z is also having 60 pages. As X and Y have same number of pages, Y and Z have same number of pages. As we have this statement, from this we can write that X and Z have same number of pages. As we got this X and Z have same number of pages, I can write that the order pair X comma Z belongs to the relation. From this, we can say that the relation R is transitive. This relation is reflexive. This relation is symmetric. This relation is transitive. Name these equations 1, 2, 3. From 1, 2 and 3, we can say that the relation R is a equivalence relation. I hope you understand solution for this question. Question number 8 in exercise number 1.1. Observe, they given one relation here. We need to show that this relation is equivalence relation. First, we will do this part. First, we will show this relation is equivalence relation. Later, we will discuss this part. As usual, in this exercise number 1.1 up to question number 7, after reading the question, we are writing 3 main points. This problem also, we will write those 3 points. First thing, this relation is on which set? You see here, this they given that there is a relation on set A. They given this is set A. Okay. Second point is they given R is a relation on set A. And how the relation is defined? Relation is defined like this. R contains order pair A comma B such that modulus of A minus B is even. You need to know which order pairs are there in this relation. As R is a relation on set A must belongs to set A, B also belongs to set A. B both are from set A and satisfies this condition. Modulus of A minus B is even. Here, writing A cross A is not a good idea. So we need to show this relation is equivalence relation. One by one we will do. First we will check reflexive condition. How to check reflexive condition? For every x belongs to A implies order pair x comma x belongs to the relation. Then I say that that relation is reflexive relation. Here, how to check it? What I'll do, instead of taking elements from set A, we'll generalize this. We'll take one element from set A. I'll name it as A. See, I taken one element from set A. This A is then, it can be 1, it can be 2, it can be 3, it can be 4, it can be 5. Okay. Now, what is modulus of A minus A? A minus A is 0. This is modulus of 0. Modulus of 0 is what? 0. So many students have doubt 0 is even or odd. 0 is clearly even. 0 is divisible by 0 is even. What I got here? I got modulus of A minus A is even. As modulus of A minus A is even, what I can say? I can say that the order pair A comma A belongs to this relation. From this, we can write that the order pair A comma A belongs to the relation. So, for any A in set A, order pair A comma A belongs to this relation. So, I'll say that this relation is reflexive. Now, we'll check symmetric condition. What is symmetric condition? Any order pair X comma Y in the relation, if Y comma X also present in the relation, then we say that relation is symmetric relation. I'll take one order pair A comma B in the relation. Here A comma B belongs to this relation means what? A comma B present in the relation means itself indicates that modulus of A minus B is even. Here when B comma A belongs to R, when I can say B comma A belongs to R, if modulus of B minus A is even, then I can say B comma A belongs to R. Here for any A and B in set A, you can observe one thing. Modulus of A minus B is same as modulus of B minus A. Here this is the basic thing you can observe. Modulus of A minus B value, modulus of B minus A value, both are same. So in place of modulus of A minus B, I can write modulus of B minus A. As we got that modulus of B minus A is even, from this I can write that the order pair B comma A belongs to relation. For any order pair A comma B in the relation, the order pair B comma A also belongs to this relation. I can say that the relation R is symmetric. Now we'll check transitive condition. What is transitive condition? Any X comma Y belongs to the relation and there exists Y comma Z also in the same relation, then we'll look that X comma Z present in the relation or not. If X comma Z is there in the relation, then we say that relation is transitive. A comma B belongs to R, B comma C belongs to R. I taken two order pairs like this. Okay, order pair A comma B belongs to R. What it means that modulus of A minus B is even. Okay, and B comma C belongs to R. What it mean? It means that modulus of B minus C is even. You need to observe one thing. I'll take one small example. A modulus of 2 minus 4 is what? It is modulus of minus 2, which is same as 2. 2 is even. Correct? Okay. Just simply calculate 2 minus 4. 2 minus 4 is what? Minus 2. Minus 2 is even or not? Yes, minus 2 is divisible by 2. Minus 2 is even. What I am trying to say, when modulus of A minus B is even, A minus B is also even. Okay. So, here, as I got modulus of A minus B is even, what I can write that A minus B is also even. Similarly, modulus of B minus C even means B minus C is even. As A minus B is even, B minus C is even. Okay, what I'll do, I'll add two even numbers. A minus B is even plus B minus C is even. Even plus even is even. Now you observe minus B plus B will get cancelled. Now what you will get? You will get A minus C is even. A minus C is even, then modulus of A minus C is also even. As modulus of A minus C is even, I can write that order pair A comma C belongs to R. You observe, I taken A comma B, B comma C in the relation. I got that the order pair A comma C is in this relation. From this, I can say that R is transitive. See, this relation is reflexive, the relation is symmetric, this relation is transitive. We'll name them. This is 1, 2, 3. From this 1, 2, 3, we can say that the relation R is equivalence relation. We proved that given relation is a equivalence relation. Now come to this part. Many students confuse to understand this. So what they are asking, show that all the elements of 1, 3, 5 are related to each other. First we will show this, right? Show that all the elements of set 1, 3, 5 are related to each other. This is one bit. And all the elements of 2, 4, set 2, 4 are related to each other. This is second bit. Third bit, but no element of 1, 3, 5 is related to any element of 2, 4. In this question only another 3 bits are there. First we will show this. Show that all the elements of 1, 3, 5 are related to each other. We need to show that all the elements of the set 1, 3, 5 are related to each other. That means what is the relation? When we say 1 is related to some other, 1 is related to 5, when we say like that, you take this relation order pair A comma B, modulus of A minus B is even. When we say the order pair A comma B belongs to relation, when modulus of A minus B is even. Here all are odd numbers. Observe difference of any two odd numbers. Suppose 1 minus 3 you take, what you will get? Modulus of minus 2, that is 2. 2 is even. Take 1, 5, modulus of 1 minus 5, modulus of minus 4, 4 is even. Like that you take any two numbers. 3, 5, you take 3, 5, 3, 5, that is modulus of minus 2, that is 2. 2 is even. We know that difference between odd numbers is even. So, all the elements of set 1, 3, 5 are related to each other. Hope you understand. When we say one element is related to other element, if it satisfies the condition difference of any two numbers in this set, modulus of difference of any two numbers is even. Clearly, difference between two odd numbers is even. So, modulus of A minus B is even. So, all the elements of set 1, 3, 5 are related to each other. Now, you see the second in this, what they are asking. All the elements of set 2, 4 are related to each other. All the elements of set 2, 4. We know that difference between two even numbers is even, right? Here you see modulus of 2 minus 4 is minus 2 is even. So what I can write? We can write that all the elements of set 2, 4 are related to each other. Now you see one more is there in this, what they are saying. But no element of this set is related to any element of this. We need to prove that no element of this set is related to any element of this set. That means 1 is not related to any one of them, 3 is not related to any one of them, 5 is not related to any one of them. The key point is this set contains odd numbers, this set contains even numbers. You take one element from this set, you take one element from this set. Suppose I'll take 3 from this, I'll take 4 from this. Modulus of 3 minus 4 is what? Minus 4 is minus 1. Modulus of minus 1 is 1. This is odd. So what the point here? Difference of an odd number and even number is odd. And each element of this related to the elements of this when it satisfies the condition modulus of A minus B is even. Modulus of A minus B, when A is taken from this set, B is taken from this set, modulus of A minus B is always odd. So we written that no element of this set is related to this. I hope you understand this solution. If you like this video, please drop a like. Share this video with your friends. In case if you are not yet subscribed to my channel, subscribe now. Exercise number 1.1, Relations and Functions chapter, class 12th mathematics. Many students feel a little difficult to understand this, but actually it is not that much difficult. You observe what they are asking in the question. Show that the relation R on this set, they given two relations here. We need to show that both are equivalence relation, and some other bit is also given. This we discuss at the end. If you observe, relation is defined on set A. What is A? I'll write that first. Before that, you observe this set A clearly. Set A contains all integers, okay? And that integer also lies in between 0 and 12. 0 is included, 12 is also included because less than or equal to they given. Na? I'm writing given set A in roster method, it may be useful. Something like this, up to 12. Actually, they given here in set builder form, I written in roster form. Okay. Second point is they given that R is a relation on the set A. Same thing I written. R is a relation on set A. Now I'll take this first relation. First we will prove that this relation is equivalence relation. This is the relation they given. Order pair A comma B says that modulus of A minus B is a multiple of 4. Here you need to understand few things. This relation contains what type of order pairs? Here, as R is a relation on set A, B, both are from set A only. Okay, you cannot take A as minus 1 because minus 1 is not in this set. A, B must be from this set only. Now, I'll prove this relation is equivalence relation. For that, first we will check reflexive condition. When we say a relation is reflexive, for every x in set A implies order pair x comma x belongs to the relation, then we say that relation is reflexive relation. Here, in place of x, I'll take A. For any A in set A, I'll check that modulus of A minus A is a multiple of 4 or not. A minus A is 0. Modulus of 0 is 0. Is 0 is a multiple of 4? When I say 0 is a multiple of 4, when I write 0 as 4 into some integer, as we know 0 is integer, 4 into 0 is 0. So, modulus of A minus A is a multiple of 4. As modulus of A minus A is multiple of 4, I can say that order pair A comma A belongs to relation. You observe modulus of A minus B is a multiple of 4, then we will say order pair A comma B belongs to relation. Similarly, modulus of A minus A is a multiple of 4 means I can say that the order pair A comma A belongs to the relation. Therefore, the relation is reflexive relation. Now, we will check this relation is symmetric or not. How to check symmetric? For any order pair x comma y in the relation, if the order pair y comma x also belongs to the relation, then we say that relation is symmetric relation. I'll take for any order pair a comma b belongs to R. An order pair a comma belongs to R. What it indicates? It indicates that modulus of a minus b is a multiple of 4. When I can say order pair b comma a belongs to R, when I can say order pair b comma a belongs to R, if modulus of b minus a is a multiple of 4, then I can say the order pair b comma a belongs to this relation. As we know this point, modulus of a minus b is same as modulus of b minus a. In place of modulus of a minus b, I can write modulus of b minus a. So, we got that modulus of b minus a is a multiple of 4. From this, we can write that the order pair b comma a belongs to the relation. So for any order pair a comma b in the relation, b comma a also belongs to R. From this, I can say that the relation R is symmetric. How to check transitive condition? You take any order pair x comma y and y comma z belongs to the relation. You take any such pair of order pairs. If x comma z also belongs to the relation, then we can say that that relation is transitive. You take a pair of order pairs a comma b belongs to R and b comma c belongs to R. You take one pair like this. Now you look that a comma c belongs to R or not. If order pair a comma c belongs to R, then we can say that this relation is transitive. As a comma b belongs to R, from this I can say that modulus of A minus B is a multiple of 4. As order pair B comma C belongs to R, from this I can say that modulus of B minus C is a multiple of 4. See here, modulus of A minus B is a multiple of 4 means A minus B is also multiple of 4. It's simple thing. See, modulus of, I'll take 8 minus 4. 8 minus 4 is 4. 4 modulus of 4 is 4. 4 is a multiple of 4. 8 minus 4 you take, that is 4, which is a multiple of 4. It can be understood easily. What I am trying to say, modulus of A minus B is a multiple of 4, then A minus B is also multiple of 4. See here, as modulus of A minus B is a multiple of 4, we can write that A minus B is a multiple of 4. Similarly, as modulus of B minus C is a multiple of 4, we can write that B minus C is a multiple of 4. So here A minus B is a multiple of 4, B minus C is also multiple of 4. If I add this A minus B and B minus C, as this is a multiple of 4 like 4x1 plus as this is a multiple of 4, 4x2. If I take 4 common, what you will get when I add these two? 4 times of k1 plus k2. Whatever you will get after adding these two numbers, that is also multiple of 4. Now you can see here minus B plus B will get cancelled. From this we can say that A minus C is a multiple of 4. If A minus C is a multiple of 4, then modulus of A minus C is a multiple of 4. When we got this modulus of A minus C is a multiple of 4, I can write that the order pair A comma C belongs to R. So what happened? For any A comma B, B comma C in the relation, I got that A comma C is also there in the relation. From this, we can say that the relation R is transitive. You observe this relation is reflexive, this relation is symmetric, this relation is transitive. From this 1 to 3, we can say that the given relation is a equivalence relation. You observe in this a small bit is there. In first bit you observe find the set of all elements related to 1 in each case. So they are asking find the set of all elements which are related to 1. First I'll write set A. What is set A? You see set A is this one 0, 1, 2, 3, 4 like that up to 12. In this set which element is related to 1? That is the question. Okay. When a particular element is related to 1 in this modulus of A minus B is a multiple of 4, then we say that A comma B belongs to R. A comma B belongs to R means A is related to B. You observe here modulus of 1. This 1 I taken from here. 1 minus, you take this number. Modulus of 1 minus 0. Modulus of 1 minus 0 is what? 1. Is 1 is a multiple of 4? No. So we cannot take 0. Now here 1 will be fixed. 1 minus, you take this one. 1 minus 1. 1 minus 1 is 0. Is 0 is a multiple of 4? Yes. So this 1 is related to 1 in set A. So they are asking us to find set of all elements which are related to 1. 1 is related to 1. Why 1 is related to 1? Because modulus of 1 minus 1 is 0. 0 is a multiple of 4. Now modulus of 1 I am taking from here minus, you take this number 1 minus modulus of 1 minus 2 1. 1 is a multiple of 4? No. So we cannot take the element 2. Like that you need to check 1 minus 3. See 1 minus 3 is modulus of minus 2 which is same as 2. 2 is a multiple of 4? No. 2 is not a multiple of 4. So we cannot take 3. Now you take 4. 1 minus 4 is minus 3. 3 which is not a multiple of 4. You take like this 1 from here and then 5. 1 minus 5. 1 minus 5 is minus 4. Modulus of minus 4 is 4. Is a 4 is a multiple of 4? Yes, 4 is a multiple of 4. So the element 5 is related to 1. I hope you are understanding. They are asking us to find set of all elements which are related to 1. This 1 is related to 1. Why? Because modulus of 1 minus 1 is a multiple of 4. 1 is related to 5 because modulus of 1 minus 5 is a multiple of 4. Like that you need to check after 5. You need to check 6. 1 minus 6 is a multiple of 4? No. 1 minus 7 is a multiple of 4? No. 1 minus 8 is a multiple of 4? No. 1 minus 9. 1 minus 9 is a minus 8. Modulus of minus 8 is 8. 8 is a multiple of 4? Yes. So 9. 1 is related to 9. Why 1 is related to 9? Because modulus of 1 minus 9 is a multiple of 4. Similarly, you check for 10. 1 minus 10 is a multiple of 4? No. 1 minus 11 is a multiple of 4? No. 1 minus 12 is a multiple of 4? No. So they are asking us to find the set which are related to 1. It is the set related to 1. I hope you understand solution for this problem. Question number 10. This problem is one of the best example in this exercise. Here, from person to person, answers will vary. You observe what they are asking in the question. Give an example of a relation. They are asking you to give an example of a relation. That relation is symmetric but neither reflexive nor transitive. You need to give an example which is symmetric, not reflexive, not transitive. Just keep in your mind what example you are trying to give. Okay, first I'll take a set A. I'll take set A like this: 1, 2, 3. From person to person, this problem will vary. I'll give one example. You try 3, 4 example for the same bit. So why I am saying this is very good question. You will get clear idea. You will get clear idea if you try for this one example. If for this one bit, if you give 5 to 6 examples for the same bit, clear idea about reflexive symmetric trans. This is the best question. In my point of view, this is the best question in these relations. Okay, I taken set A and I am saying that R is a relation. R is a relation on A. I'll define a relation like this. R equal to, as they are saying it is symmetric, I'll take like this: 1, 2, 2, 1. Because in the question they are asking, show that it is symmetric but not reflexive, not transitive. Okay, you observe, is this relation is reflexive? In exam, in your board exam, you need to write steps like this: reflexive. For 1 is there in set A, 1 is there in set A, but 1, 1 does not belongs to the relation. 1, 1 is there in this relation? No. Because of this reason, I can say that this relation is not reflexive. Now, is this relation is symmetric? You need to check like this. You take order pair 1, 2. For this order pair 1, 2, 2, 1 exist in this relation? Yes, 2, 1 exist in this relation. For the order pair 2, 1, the order pair 1, 2 exist in this relation? Yes, order pair 1, 2 exist in this relation. That means for every A comma B in the relation, B comma A exists in the relation. What way you write this in board exam? You need to write like this: for every order pair A comma B belongs to R implies B comma A belongs to R. Therefore, R is symmetric. I hope you understand. Now, transitivity. You observe this relation. There exists A comma B, B comma C. But A comma C does not belongs to the relation. What is A comma C? 1, 1. When it is not transitive, best thing is given counter example. This is what we are discussing from the beginning of this, right? So what I'll write, when it is not transitive, give example. For 1, 2 belongs to R and 2, 1 belongs to R, that implies 1, 1 does not belongs to the relation. Therefore, R is not transitive. So, if you observe, this relation is not reflexive, not transitive, but this relation is symmetric. What they are asking in the question? Give an example of a relation which is symmetric but neither reflexive nor transitive. See, I given one example like this. I want you to try another 2 to 3 examples of your own so that to get clear idea about this relations topic, right? So, this 10th question is very useful question to understand this concept. Okay, you observe this second bit. You need to find an example of a relation. That relation is transitive but neither reflexive nor symmetric. This is actually very interesting, right? I'll try to confuse you. Let's see whether you will confuse or not. I'll take a set A as 1, 2, 3. R is a relation on A and the relation is defined like this: order pair 1, 2. That's it. Now, is this relation is reflexive? No, because 1 is there in set A, 1, 1 is not in the relation. That's why this relation is not reflexive. 1, 2 is there in the relation. 2, 1 does not belong to the relation. So, this relation is not symmetric. So, clearly this relation is not reflexive. This relation is not symmetric. Is this relation is transitive? 100% this relation is transitive. Every time it creates so much headache to convince the student that this relation is transitive. Why this relation is transitive? What is transitive definition? If A comma B belongs to R and B comma C belongs to R, then we look that A comma C belongs to R. If such things happen, then we say that relation is transitive. Whenever, one more thing is, whenever you cannot find such pair of order pair, when you cannot find A comma B, B comma C in the relation, no need to look for A comma C. In that case, we say that that relation is transitive, right? In earlier examples also we discussed the same thing, right? Here, to check there doesn't exist a comma b, b comma c in the relation, to check a comma c. There doesn't exist a comma b, b comma c in this relation. That's why this relation we say it as a transitive, right? If I want you to make happy, I can give the one more example, easy example like this: 1 comma 1, 1 comma 2, 2 comma 3, 1 comma 3. If I take like this relation is not reflexive because 2 comma 2 does not belongs this relation. This relation is not symmetric because 1 comma 2, 2 comma 1 does not belongs the relation. This relation is transitive. You can check for every a comma b, b comma c, there exists a comma c. You see here 1 comma 1, 1 comma 2. 1 comma 2, right? This ends with 2, 1 comma 2, 2 comma 3. 1 comma 2, 2 comma 3 is 1 comma 3, right? See, 1 comma 3, nothing starts with 3. 1 comma 3, nothing starts with 3. Every order pair satisfying transitive condition. Why I am saying this bit is very important. If you can give, I given this example. You give 4-5 examples like this, you will get clear idea about this transitive, reflexive, symmetric, right? Okay. So in board examination, how you will write the steps? Reflexive, very simple. The element 1 is there in set A, but 1 comma 1 is not in the relation. That's why this relation is not reflexive. Clear? Okay. Symmetric, you see order pair 1 comma 2 is there, 2 comma 1 does not belongs to the relation. That's why this relation is not symmetric. For the order pair 1 comma 2 belongs to R implies the order pair 2 comma 1 does not belongs to the relation. Therefore, R is not symmetric. This is interesting. How you write in board exam that this relation is transitive? First point is this relation is transitive. Yes, this relation is transitive. How you will write this in the solution? For every a comma b belongs to R, there doesn't exist b comma c belongs to R. For a comma b, if b comma c also exists in the relation, then we will check a comma c. If there doesn't exist b comma c in that relation, in that case directly we say that that relation is transitive. I hope you understand this solution. I don't give any written notes for this example. I'll just give an example and we'll discuss. I want you to write the notes your own. I'll take set A as 1, 2, 3 and R is a relation on A, and I'll define the relation like this. What they are saying, this relation is reflexive. As they are saying this relation is reflexive, 1 comma 1, 2 comma 2, 3 comma 3. These 3 order pairs must exist in the relation, right? These 3 order pairs must exist in the relation. Then only it is reflexive. Otherwise, it is not reflexive. Okay. As they are saying it is symmetric, if I take order pair 1 comma 2, 2 comma 1 must exist, right? If I take 1 comma 3, 3 comma 1 must exist. I taken a relation like this. Now, you check it satisfies this condition or not. Reflexive. Is this is reflexive? Yes. For 1 belongs to A, 1 comma 1 belongs to R. For 2 belongs to A, 2 comma 2 belongs to R. For 3 belongs to A, 3 comma 3 belongs to R. If I take order pair 1 comma 2, 2 comma 1 also exists. If I take order pair 2 comma 1, order pair 1 comma 2 belongs to R. So this order pair satisfies symmetric condition. See, these elements, you know, these elements always satisfies reflexive, symmetric, transitive condition. No need to check. These are dummy elements, right? No need to check these things. These elements always reflexive, these elements always symmetric, these elements satisfies transitive condition, right? Now you look at here 1 comma 3, 3 comma 1, both are there. So 100% this relation is reflexive, 100% this relation is symmetric. Now not transitive. To say it is not transitive, we need to give one example. You look at this 2 comma 1, 1 comma 3. There exists a comma b, b comma c. 2 comma 1 belongs to R and 1 comma 3 belongs to R. 2 comma 3 is there in the relation. Check it. In the given relation, 2 comma 3 is there. 2 comma 3 does not belongs to the relation. So this relation is reflexive symmetric, but this relation is not transitive. So this is the example for the given question. They are asking you to give an example which is reflexive symmetric but not transitive. No? This is the example. I hope you understand this. Give an example of a relation which is reflexive, transitive but not symmetric. You observe I taken set A and R is a relation on A. Okay. I'll give an example. In the question, as they are saying, this relation is reflexive 1 comma 1, 2 comma 2, 3 comma 3. These elements must exist. And they are saying that this relation is transitive also. Actually, if I stop here, you know that this relation is a equivalence relation. This is reflexive, symmetric and transitive also. But they are saying it is not symmetric. As they are saying it is not symmetric, I'll add this 1 comma 3. Okay. If I stop here, is it is the example? We'll check. Reflexive, yes. For 1, 1 comma 1. For 2, 2 comma 2. For 3, 3 comma 3 exists. So this is reflexive. Transitive. See, whenever you check transitive condition, no need to check these elements, right? If you, even though if you take this order pair and you check with any other order pair, it always satisfies. Suppose 1 comma 3, 3 comma 3, A comma B, B comma C is what? A comma C, that is 1 comma 3. 1 comma 3 is there here only, right? This relation is transitive. This relation is reflexive. This relation is transitive. See, very simple. See, these, if you start from here, this ends with 1. Any other starts with 1? Yes, here. 1 comma 1, 1 comma 3. A comma C is what? 1 comma 3. That's why we won't check these elements. It's waste of time. These elements always reflexive, always symmetric. These elements, when we pair with a transitive condition, that also satisfies. Right? This ends with 2, no other order pair starts with 2. This ends with 3, no other order pair starts with 3. So here what happened? This relation is reflexive, this relation is transitive, this relation is not symmetric. Why it is not symmetric? 1 comma 3 is there in this relation, but 3 comma 1 does not belong to the relation, right? I want you to write the steps for this, right? I'll stop this here. You please write the notes neatly. Give an example of a relation which is symmetric and transitive but not reflexive. Okay, you observe here, I taken set A and R is a relation on A. Okay, I'll take a relation like this, order pair 1 comma 1. That's it. Is this relation is reflexive? Is this relation is reflexive? See, or for 2 is there in set A. 2 comma 2 does not belongs this relation. So this relation is not reflexive. We want example which is not reflexive. Okay. Symmetric 1 comma 1. Yes, for 1 comma 1, reverse order 1 comma 1. This type of elements A comma A, B comma B, C comma C, this type of elements always satisfy symmetric condition. Okay. Transitive for A comma B, B comma C doesn't exist, right? Or else 1 comma 1, 1 comma 1, 1 comma 1 only. This type of elements always satisfies transitive condition also. So this relation is not reflexive, this relation is symmetric, this relation is transitive. I want you to write the notes neatly. See, this is, once again I am saying, this question is very interesting question, right? You give your own example. If you take this bit, try to give 5 examples of your own. Take this bit, try to give on 5 examples. Like that, by the time you will complete, you will get 25 examples, right? I don't say that you will get any confusion later related to reflexive, symmetric, transitive, right? This is very good question. Please try your one. Question number 11. You first try to understand what is the data in the given question. See, they are saying that the relation R in the set A. What is set A? A of points in a plane. What they are saying, A is set of all points in a plane and R is a relation on A. First, we'll write this information. A is set of all points in a plane and R is a relation on A. R is a relation on A. How the relation is defined? You observe here, 2 points P comma Q. What way they related? The distance of P from origin. The distance of P from origin means OP is same as the distance of Q from origin. The distance of Q from origin is OQ. OP is same as OQ they given. So I'll write this relation. To understand it bit easier, I'll write this relation like this. There are 2 points P comma Q which are related when OP equal to OQ. If OP equal to OQ, then P comma Q are related to each other. Suppose OP1 is not equal to OP2, then P1 comma P2 belongs to this relation. P1 comma P2 does not belong to the relation. When P1 comma P2 belongs to the relation, when OP1 is equal to OP2, then only the order pair P1 comma P2 belongs to the relation. See, understanding the relation is important. Okay, we need to show that this relation is equivalence relation. Look at this. Show that this relation is a equivalence relation. When we say a relation is a equivalence relation, if it is reflexive, symmetric and transitive, then we say that relation is a equivalence relation. Reflexive relation. When we say this relation is reflexive, suppose for any point P in set A, if the order pair P comma P belongs to the relation, then we say that relation is reflexive relation. When P comma P belongs to R, when OP equal to OP. Is OP is same as OP? Yes, the distance from O to P is same as the distance from O to P. A very simple thing it is, right? So the order pair P comma P belongs to the relation. How to write this relation? For any point P belongs to A implies OP is same as OP. This tells you that the order pair P comma P belongs to the relation. Therefore, R is a reflexive relation. Symmetric relation. To check symmetric relation, first I'll take an order pair P comma Q belongs to the relation. I taken order pair P comma Q belongs to R. If I can prove that Q comma P belongs to R, then I can say that this relation is a symmetric relation. As I taken the order pair P comma Q belongs to R, from this I can write that OP equal to OQ because P comma Q are related. This tells you that the distance from O to P, the distance from origin to point P is same as the distance from origin to point. When OP is equal to OQ, can I say OQ equal to OP? It's simple thing actually, no need of much discussion. If OP equal to OQ, then obviously OQ equal to OP. We can write like so. From this, what I can write? Q comma P belongs to R. When Q comma P belongs to R, when OQ equal to OP. Here it is very clear that OQ equal to OP. So this tells you that Q comma P belongs to R. So if you take any order pair P comma Q, for any order pair P comma Q, Q comma P also belongs to R. Therefore, this relation is a symmetric relation. Now I need to check a relation is transitive or not. For that, what I'll take two order pairs. P comma Q exists, it belongs to the relation R, and Q comma R, Q comma S belongs to the relation R. See, I taken P comma Q, Q comma S belongs to the relation. Now I need to check P comma S is there in the relation. As I taken the order pair P comma Q belongs to R. From this, I can write OP equal to OQ. And as I taken Q comma S belongs to R, I can write OQ equal to OS. Okay. So if you observe this, OP equal to OQ, OQ equal to OS, OQ equal to OS. From this, what I can say? I can say OP equal to OS, OP equal to OS. This tells you that the order pair P comma S belongs to the relation. So for P comma Q belongs to R and Q comma S belongs to R, P comma S also belongs to R. This works for any such order pair, right? Therefore, the relation R is transitive. You see, this is reflexive relation, symmetric relation, transitive relation from 1, 2 and 3. From these three equations, we can say that given relation is equivalence relation. If you observe this question, at the end, they given a small part. See here, after this, we prove till here, it is a equivalence relation. You see what they are asking? Further, show that set of all points related to point P. Here they are saying P is not origin. Set of all points related to point P is a circle passing through P with origin as center. If you observe what they are asking, show that set of all points related to point P is a circle passing through P with origin as center. You try to understand this with the help of a diagram. Suppose origin as a center. There is a point P. You suppose this OP is equal to K units, right? You know from the definition of circle, if you take any point, suppose I'll take this as Q1. Q1 is a point on the same circle. What is OQ1? Is OP is same as OQ1? Yes, because it is a circle, right? And here P comma Q1 belongs to the relation. Okay, if I take another point Q2, what is OQ2? OQ2 is also K because it is a circle, this is the radius. So whatever points you take which are related to point P, try to understand what way it is related. Whatever points I am taking here, Q3, Q4, Q5, Q6, Q8, Q100, whatever points, these are all related to point P as per this relation. Why? Because OP equal to OQ1, OP is equal to OQ2, equal to OQ3, equal to OQ100. Like so, if we take all such points as these all Q1, Q2, Q3 are related to point P, if you observe all such points forms a circle. That circle passes through P with the origin as center. I hope you understand. You observe, I considered OP equal to K. Suppose O is center of this O is center, OP equal to K. You take n points such that OP equal to OQ1, OP equal to OQ2, OP equal to OQ3, OP equal to OQN. Here it tells you that P comma Q1 are related, P comma Q2 are related, like that P comma Qn are related. If you observe all such points, if you join all such points, all such points forms a circle. That circle passes through point P and O as a center. It can be understood easily. This tells you that Q1, Q2, Q3 and so on, Qn forms a circle which passes through, that circle passes through P with center origin. In this question, they are asking, show that the set of all points related to point P is a circle. These are all the points related to point P. You can observe from the definition of circle, as they are related to point P, this forms a circle. That circle passes through point P with center 0, 0. You observe this question number 12. Show that the relation R defined on set A of triangles. That means A is set of all triangles, R is a relation on A. A is set of all triangles, R is a relation on A. R is a relation defined that the order pair T1, T2 belongs to R if T1 is similar to T2. The triangle T1 is similar to T2, then T1, T2 belongs to R. Suppose T3, T4. When this order pair belongs this relation? When? If the triangle T3 is similar to triangle T4, then T3, T4 belongs to R. Suppose T1, T5 are not similar triangles. T1, T5 are not similar triangles. Then T1, T5 belongs this relation or does not belongs this relation. If these triangles are similar, then only belongs the relation. Otherwise, we say that the triangles does not belongs to this relation. Okay, they are saying that show that this relation is equivalence relation, and some other extra information is there that we will discuss at the end of this solution. First, I'll prove that there is a relation on A. That relation is equivalence relation. Okay. When I say this relation is an equivalence relation, it is reflexive, symmetric and transitive. Then we say this relation is a reflexive relation. See, when we say this relation is reflexive, if we take any triangle T, if the order pair T, T belongs to the relation, then we say that relation is reflexive. Here T is a triangle. Triangle T is similar to triangle T. Actually, T is the same triangle. Every triangle similar to itself. We can say like this. Suppose you and your image are similar or not? Similar, right? So, what I'll write here, for any triangle T belongs to A implies T is similar to T. As T is similar to T, we can say that the order pair T, T belongs to the relation R. Therefore, the relation R is reflexive. Now, this relation is symmetric or not. To prove the relation is symmetric or not, first I'll take T1, T2 belongs to the relation. I suppose there exist two triangles as that T1 is similar to T. If I can prove that T2, T1 belongs to the relation, then I can say that this relation is a symmetric relation. As I taken T1, T2 belongs to R, from this I can write that T1 is similar to T. If T1 is similar to T2, then can I say that T2 is similar to T1? If T1 is similar to T2, T2 is also similar to T1. It's a simple logic, no need of much discussion here, right? So I can say that T2, T1 belongs to R. So here, for any T1, T2 belongs to R, T2, T1 also belongs to R. Therefore, the relation R is symmetric. Next, transitive relation. What I'll do, I'll take an order pair T1, T2 belongs to R and T2, T3 belongs to R. Now I need to check T1, T3 belongs to R or not. As T1, T2 belongs to R, I can write that T1 is similar to T2 and T2 is similar to T3. T1 is similar to T2, T2 is similar to T3. If T1 is similar to T2, T2 is similar to T3, can I say that T1 is similar to T3? It's a simple one, right? It is easiest one actually. From this, I can say that T1 is similar to T3. If T1 is similar to T3, I can write that T1 comma T3 belongs to the relation. Therefore, the relation R is transitive. You observe this relation is reflexive, this relation is symmetric, this relation is transitive. I'll name them as 1, 2, 3. From these three equations from 1, 2 and 3, we can say that R is a equivalence relation. From 1 to 3, we can say that R is a equivalence relation. You observe some other data is there in the question. You observe they are saying three right angle triangles. T1 is a triangle with sides 3, 4, 5. T2 is a triangle with sides 5, 12, 13. T3 is a triangle with sides 6, 8, 10. Which among these three triangles are related? Right? I'll write here. Here, three triangles are there. This is the triangle with sides 3, 4, 5. This is the triangle with sides 5, 12, 13. This is the triangle with sides 6, 8, 12. Which triangles are related to each other? If two triangles are similar, then we know that corresponding sides are proportional. For example, if we take T1, T2, 3 by 5 equal to 4 by 12 equal to 5 by 13. Is it true? This is 1 by 3. 1 by 3 is not equal to 3 by 5. So, T1, T2 are not similar triangles. You check T1 and T3. T1 and T3. T1, T3, 3 by 6, 4 by 8, 5 by 10. You see 3 by 6 is 1 by 2, 4 by 8 is 1 by 2, 5 by 10 is also 1 by 2. They are all equal to 1 by 2. So this tells you that the sides of first triangle and third triangle are proportional. They are all equal to 1 by 2. So from this I can say that T1 is similar to T3. As these two triangles are similar, T1, T3 belongs to the relation. That means the triangle T1, T3 are related to each other. I hope you understand this solution. Question number 13. Show that the relation R defined in the set A of polygons. A is set of all polygons. R is a relation on A, and the relation is defined like this: P1 comma P2 such that P1 P2 have same number of sides. We need to show that it is a equivalence relation. Further, some data is also given. We will discuss this at the end of the solution. First, I'll write the given information. A is set of all polygons. R is a relation on A. And how this relation is defined? An order pair P1 comma P2. Polygon P1, polygon P2 have same number of sides. What is polygon? A closed figure formed with three or more sides is called a polygon. Suppose you see here, this is the closed figure found with three lines. Here, this is one polygon. This polygon is known as triangle, right? This is the closed figure formed with four lines. So this closed figure is known as one polygon. Here, number of sides in this polygon is 4. So it's a quadrilateral or parallelogram, whatever it is. What is polygon? A closed figure formed with three or more sides: pentagon, hexagon, like that, all are polygons. Okay, now we need to show that this relation is equivalence relation. Okay, reflexive relation. When we say this relation is a reflexive relation, I'll take a polygon P in set A. For any polygon P in set A, when I say P comma P belongs to R, this polygon have same number of sides. Actually, P is same now. So number of sides of polygon P and number of sides of polygon P are same. Try to understand, please. Here, best method is the polygons P and P have same number of sides. From this, we can write that the order pair P comma P belongs to R. Therefore, the relation R is reflexive. Now, symmetric relation. Let P1 comma P2 belongs to the relation. Now, if you can prove that P2 comma P1 also belongs to the relation, then we say this relation is symmetric relation. As I taken P1, P2 belongs to R, from this I can write that polygons P1 and P2 have same number of sides. If polygons P1, P2 have same number of sides, from that can I say that the polygons P2 and P1 also have same number of sides? Obviously, these are the easiest things, no need to discuss much. P1, P2 have same number of sides means P2, P1 also will have same number of sides, right? As we got P2, P1 have same number of sides, from this we can write the order pair P2 comma P1 belongs to R. So for any P1 comma P2 belongs to R, P2 comma P1 also belongs to R. Here I'll write for any. So therefore, for any order pair P1 comma P2 belongs to R implies the order pair P2 comma P1 belongs to R. This tells you that the relation R is symmetric. Transitive relation. To prove this relation is transitive relation, I'll take P1 P2 belongs to R and P2 P3 also belongs to R. Now I need to prove that P1 P3 belongs to R. If P1 P3 belongs to R, then I can say that if the order pair P1 and P3 belongs to R, then I can say that this relation is transitive. This tells you that P1 P2 have same number of sides. This tells you that P1 P2 have same number of sides, and this tells you that P2, P3 have same number of sides. See, P1, P2, polygons P1, P2 have same number of sides. Polygon P2, P3 have same number of sides. Can we say that P1, P3 are having same number of sides? Actually, we cannot discuss much here. If I discuss much here, it's just insulting to you, right? P1, P3 have same number of sides or not? Yes, P1, P3 are having same number of sides. It can be understood easily because you see P2 is there here, P2 is there here, right? These two polygons have same number of sides. These two polygons have same number of sides means the polygons P1 and P3 are also having same number of sides. Polygons P1, P3 have same number of sides. From this, I can write the order pair P1 comma P3 belongs to the relation. This tells you that the relation R is transitive. If you observe that relation is reflexive, I'll take it as equation 1. This relation is symmetric, I'll take it as equation 2. This relation is transitive, I'll take it as 3. From 1, 2 and 3, we can say that the relation R is equivalence relation. If you observe in the question, at the end some other information is there. What is the set of all elements in A which are related to a triangle T with sides 3, 4, 5? A contains what? A contains all polygons. Polygons means what? In this triangles are there, parallelograms are there, quadrilaterals are there, pentagon is there, hexagon is there, all the things are. Which elements of set A related to this particular triangle? See here, they are saying there is a triangle with sides of length 3, 4, 5. One side of a triangle is 3, another side of a triangle length 4, 5. This is one triangle. By seeing this 3, 4, 5, you can easily say that it is a right angled triangle. This triangle contains how many sides? Obviously, when I say it is a triangle, it contains 3 sides. What elements of set A related to this triangle? Set A contains all polygons. In set A, triangles are there. Yes, set A, triangles are there, quadrilaterals are there, all polygons are there. So, all the triangles of set A are related to this triangle. What way it is related? Suppose I'll take T1 is a triangle from set A. Okay. T is a triangle with sides like this 3, 4, 5. Is T1 comma T belongs the relation when T1 comma T belongs the relation when the T1 and T are both are polygons because triangle is a polygon. T1 and T are have same number of sides. Number of sides is important here, not the measure of the sides. Number of sides. When the triangle T1 and triangle T belongs to the relation when both have same number of sides. Triangle T1, triangle T both are having same number of sides. Obviously they are related. So this is the easiest one. All the triangle of set A, all the triangles of set A are related to triangle T with the sides 3, 4, 5. I hope you understand this. You see this question number 14. L is set of all lines in xy plane. Why they are saying set of lines in xy plane? It is a two-dimensional geometry. You know in three-dimensional geometry also straight lines are there. It's a two-dimensional geometry. Okay. R is a relation on L. How this is defined? Order pair L1 comma L2. L1 is parallel to L2. Show that this relation is a equivalence relation. First, I'll write the given data and I'll show that R is a equivalence relation. At the end, we'll discuss the small part also. You see, L is set of all triangles in xy plane. R is a relation on A and the relation is defined like this. The order pair L1 comma L2 belongs to R if L1 is parallel to L2. First, we'll show that this relation is a equivalence relation. For that, we'll prove this relation is reflexive. What I'll do for any L1 belongs to L. L is what? Set of all lines. I taken one line. I named it as L1. Okay, is L1 is parallel to L1? We know that we can say that every line is parallel to itself. We can say like that. Every line is parallel to itself, right? So L1 is parallel to L1. L1 is parallel to L1 means L1 comma L1 belongs to R. From this, we can say that R is reflexive. We'll name this as equation 1. Okay, symmetric relation. For that, I'll take one order pair L1 comma L2 belongs to the relation. When order pair L1 comma L2 belongs to R, as I written L1 comma L2 belongs to R, this itself says that L1 L2 are parallel. Lines L1 and L2 are parallel. If lines L1 and L2 are parallel, what do you say about L2 and L1? 100% they are parallel. See, this is the line L1. Okay, this is parallel to line L2. If L1 is parallel to L2, L2 is also parallel to L1. Is the no need of much discussion, right? Okay, from this, what L2 and L1 are parallel. From this, I can write L2 comma L1 belongs to R. This tells you that this relation is symmetric. You name it as equation number 2. Now transitive. To check transitive condition, what I'll do, I'll take two order pairs L1 comma L2 belongs to R and L2 comma L3 belongs to R. If you observe this, L1 L2 are parallel. As L2 L3 belongs to R, L2 comma L3 also parallel. It can be understood easily. You see, L1 is parallel to L2, L2 is parallel to L3. What do you say about L1 and L3? Are they parallel? It is easy. If L1, L2, L3 are parallel, then obviously L1, L3 are parallel. So this tells you that L1 and L3 are parallel. This tells you that the order pair L1 comma L3 belongs to the relation. Therefore, the relation R is transitive. We take it as equation 3. See, we know that this relation is reflexive. We know that this relation is symmetric. We know that this relation is transitive. From 1 to 3, R is a equivalence relation. You observe they are asking find set of all lines related to this line. Find set of all lines related to this line. Okay, this is the given line y equal to 2x plus 4. This is the line y equal to 2x plus 4 is one line. In the question what they are asking, find the set of all lines which are related to this line. Which line is related to this line if those two lines are parallel, right? I hope you understand. You need to find all the lines which are related to this line. From straight lines chapter, you know that y equal to 2x plus c. I'll take like this. You see, what is slope of this line? This is in the form of y equal to mx plus c, right? So slope of this line is 2. What about this? This is also in the form of y equal to mx plus c. Slope of this line is 2. So this tells you that these two lines are parallel. What is C? C is any arbitrary constant. In place of C, you can write 1 by 2. In place of C, you can write 3. In place of C, you can write 4. C is any arbitrary constant, right? So, these lines are related to this. In place of C, if I write 5, now, is these two lines are related? Yes. Why? Because they are parallel. So, the set of all lines y equal to 2x plus 4 are related to this line. This is not one line. This contains many lines. If I change C value, different lines I'll get. Whatever the lines we'll get from that, all those lines are related to this. Why I am saying all those lines are related to it? Because whatever line comes from this, suppose y equal to 2x plus 100, that line, this line are parallel. As per the relation, if two lines are parallel, they are related in this question, right? You see, this is a multiple choice question. They are asking us to choose the correct answer. They are saying that one set is there 1, 2, 3, 4. R is a relation on this set and the relation is defined here. Okay, so choose the correct answer. If you observe, reflexive, symmetric, transitive, like that it is there. See, in this objective part of relations, elimination method is the best method actually, right? So first we will check the reflexive relation. When this relation is reflexive, you see 1 comma 1, yes, 1 comma 1 is there. 2 comma 2, yes, 2 comma 2 is there. 3 comma 3, yes, 3 comma 3 is there. Next, for 4, 4 comma 4. Clearly, this relation is reflexive. Now observe the options. Is there any options which is saying that this relation is not reflexive? You remove that. You see reflexive, reflexive, not reflexive. So we can remove this third option. In third option, they are saying it is not reflexive, but when we check, it is a reflex. Okay, symmetric. For 1 comma 2, 2 comma 1 is there in this relation. For 1 comma 2, 2 comma 1 is not there in this relation. This relation is not symmetric. Why? 1 comma 2 is there in the relation. When 1 comma 2 is there, 2 comma 1 must present in the relation. If this fails, then directly we can say it is not symmetric. Right? 2 comma 1 is there, not there. So this relation is not symmetric. You observe here, elimination method. First option saying it is symmetric, but actually it is not symmetric. So you can eliminate this first option. You see here, last option says that it is a equivalence relation. Equivalence relation means it is symmetric, but actually given relation is not symmetric. So we can eliminate this. So obviously this option B is the correct option. If you want, you can check the transitive condition. As it is a multiple choice question, only one option correct things are there. 100% option B is the right option. If you want, you can check the transitive condition. You observe the question. R is a relation on set of all natural numbers, and it contains order pairs such that A equal to B minus 2 and B is greater than 6. Okay, choose the correct answer. As they are saying B is greater than 6, these are all order pair A comma B. These are all order pair A comma B. B is greater than 6. You see here, this B is not greater than 6, so we can eliminate this option A. B is greater than 6. Okay, B is greater than 6. Okay, what is A? A is B minus 2. Here we will go with the verification method only, options wise. B is what here? B is 8. You put B is 8 in this. A equal to 8 minus 2. A is 6. Actually 6 comma 8 belongs this relation, not 3 comma 8. Here you can easily eliminate this 3 comma 8. Now you see here, just now we just calculate, this is A comma B na. First point, B is greater than 6. Okay. In place of B, if I write 8 here, 8 minus 2 is 6, you will get A value. When A is 6, B is 8. So clearly option C is there in the relation. You observe this 8 comma 7. Here when B is 7, put B is 7 here. A equal to B is 7 minus. This is A is 5. Actually 5 comma 7 belongs to R, not 8 comma 7. So this is wrong option. So obviously correct option is this third option. I hope you understand. See, creating these videos taken so much of time. I strongly recommend you to please drop a like. If you felt these videos are useful, please share it in your WhatsApp group. Thanks for watching. Take care. Bye bye.